By the end of this video, you'll have learned how to solve every single geometry and trigonometry question on the SAT, which is about 14.2% of the math section according to my latest statistics. Now, for geometry and trigonometry questions, I break it down into 6 different types of questions, which we're going to go over in order in this video. And each of these types of questions builds off of the knowledge from the previous one. So to know area and volume, you need to know a bit of similar shapes and right triangles and angles, lines, and triangles questions. And in case you were curious, I think a lot of people would be interested in this, I also have the distributions of the types of questions between Module 1 and the hard second module. And if you don't know, the SAT is adaptive, and there's Module 1 and Module 2 for the reading, writing, and the math section. If you do well in Module 1, they'll give you a harder second module. If you don't do well in Module 1, they give you an easier second module. This is just for the hard second module, because if you watch my stuff, you're going to get the hard second module anyways. Okay. First of all, you'll notice the geometry and trigonometry questions in Module 1 surprisingly is higher than it is for Module 2. You see less of these in Module 2. But the difference is these are going to be a lot harder questions. You notice the easier types of patterns, there's a lot more of those in Module 1, there's a lot less of them in Module 2. But enough of that, let's jump straight into the first type of question, which is angles, lines, and triangles. For angles, lines, triangle questions, you need to know these 7 patterns and be able to recognize them really well. But don't worry, because these are pretty easy and you probably know most of them or all of them already. Okay, the first thing is vertical angles, which is basically any time straight lines intersect each other, during that intersection, the angles right across from each other are the same. So for example, this angle is the same as this angle because it's right across from each other. This angle is going to be the same as this angle because they're right across from each other. Okay, and it doesn't just have to be 2 lines either. It could be multiple lines. Let's say there's 3 lines. At the intersection, sorry, that's a bad line, but at the intersection of these lines, like this angle is the same as this angle because it's the angle right across from each other. However, this angle is not the same as this angle because this angle is not across from that angle. Okay, this angle is across from this angle. So it's only these 2 angles that would be the same then. Okay, you don't know for certain that this is the same as that one. Even if it looks the same, it's not one of the patterns, so you can't use it. Okay, it just has to be one of the 4 patterns that we go over. And the next pattern is supplementary angles, which is the idea that if there's a bunch of angles on a line, then all these angles add up to 180 degrees. Okay, so let's say this is only 2. There could be multiple. Okay, let's say there's 3 angles, right? This angle, this angle, and this angle. If you add up all 3 of these angles, they should add up to 180 degrees. Because if you think about it, the angle of a straight line is 180 degrees, right? This from here, that's 180 degrees. So it makes sense that all these should add up to 180 degrees. But just memorize that. Okay, you should be able to recognize that pretty easily too. Okay, if there's a bunch of angles on a line, they add up to 180 degrees, and you can use that to find. Let's say we know this angle and we know this angle, but we don't know this angle. Then we can just do 180 minus these 2 to get this one. Okay, so it's a bit messy, but we'll move on. The next one is corresponding angles. And these only work with parallel lines. Okay, and you know the parallel, because the question tells you it. Or also if you see these symbols, which is like arrow marks on the 2 angles, that means these 2 are parallel to each other. If you see arrow marks and the arrow marks on 2 lines, they're parallel to each other. Okay, just because they look parallel doesn't mean they're parallel. The question actually has to say that they're parallel. And this is called corresponding angles. Okay, and it's an easy way to memorize this. It's just the corresponding angles, where the angles on the same spot on the 2 different parallel lines are the same. So this angle is the exact same spot, right? The top right of this parallel line and the top right of this parallel line. Okay, these are the exact same spots on 2 different parallel lines. That means they're the same. It has to be on the same line that intersects both of them though. But there's a line that intersects both of the parallel lines on the same spot of the intersection between the 2 parallel lines. Those are the same. So if there's another line here, then you can't say for certain that this angle is the same as like this angle, for example, or this angle is the same as this angle. Unless we were told that these are parallel lines, and then we'd be, oh, it's because this line intersects both of them, then oh yeah, they're the same spot, so it's the same. But if we don't know that these are parallel lines, then it's not. Okay, I'll make this simple. And it doesn't just have to be this specific spot, it could be any of them. It's like this angle is the same as this angle is the same as this angle, because they're the same spot, right? The bottom left corner of this intersection between the 2 parallel lines, these are corresponding angles, okay? So they're the same. Now the last pattern, I just want you to know this. You technically don't need to memorize this as a separate pattern because you can derive this pattern from the other stuff we went over. And the pattern is alternate interior angles. Interior angles, by the way, is just the angles on the inside. Go figure, right? So these are the angles on the outside, that doesn't matter. So the angles on the inside. Okay, the inside stuff, okay? The inside angles, the ones that alternate are the same. That's why it's called alternate interior angles. So this angle is on the inside and this angle is on the inside, and they'll alternate, like they'll right across from each other, right? They're alternate angles, so they're the same. Okay, and you can technically get this from corresponding angles and vertical angles. For example, I know this angle is the same as this angle, right? And I know these two angles are vertical angles because there's two straight lines intersecting each other. So obviously the angles across from each other are the same. So we already know that this angle is the same as this one. But I just want you to memorize this as a separate pattern just so you can recognize it faster. Because this is pretty common. You see this a lot on the SAT. So these are the same angles, alternate. So also same thing, like this angle is the same as this angle, right? Because they're interior angles and they're alternate. Also, you don't see this a lot, but it technically also goes for these angles, right? The alternate exterior angles, I guess, are the same as well. Because it's the same theorem, right? This angle is the same as this angle because they're corresponding angles, and vertical angles to that one is this. So basically, the idea is you can't just guess if angles are the same or not. You have to prove the angles are the same by using one of these four patterns. If it's not one of, this just has to do with lines, okay? No shapes involved, just lines by themselves. If you see lines, then you have to know, you have to prove it that those things are the same. You can't just assume they're the same because they look the same on the SAT. Okay, and these two have to do parallel lines, okay? It only happens if they're parallel lines. These don't really matter. It's just like anywhere you see them, okay? But this is only for parallel lines. The question has to give away that those two lines are parallel to each other. Now let's go over triangles. And this is just for regular triangles. This isn't right triangles or anything like that. It's just normal triangles, or triangles in general. Okay. And you probably already know this, but all the angles in a triangle add up to 180 degrees. This is also in the reference sheet, by the way. On the SAT testing software, if you click on reference, the reference sheet pops up. And you'll notice at the very bottom, it says all the angles in the triangle has to add up to 180. So we know this angle plus this angle plus this angle, right? These three angles, and they add 180 degrees. So we just need to know two of them to get the total one. Okay, this is a helpful pattern to know. If you're stuck, you should probably use triangles. If you can find a triangle in there somewhere, which I'll show example questions on later on, but you just need to know, okay, let's say I know this angle, I know this angle, I can just do 180 minus these two angles to get the last one, because they add to 180 degrees. Okay, that's just like strategy. You should recognize that pattern. Okay, or you should know to look for that. Another thing is isosceles triangles, which is really common. Isosceles triangles is just anytime we know two angles or lengths of the triangles are the same. So, for example, this one, right? This triangle, so let me get rid of previous thing. Okay, this triangle is telling us, by the way, the slashes just means the sides are the same. Okay, like the number of slashes, right? So if I had this is the same as this one. Right? If I had like another triangle and I said 1 slash there, so this one has the same amount of slashes as this one, so that means these two are the same. Same thing if I said like 2 slashes here and I said this one has 2 slashes as well. Since these two have the same amount of slashes, then I know this is the same length as this one. Okay, so that's just what the slashes mean, in case you see that. Same thing with like you might notice me doing the angles earlier. It's the same thing. Like this has only one arc, then this is the same, and then I put another arc here. So these both have only one arc, so they're the same angle. If I said these have 2 arcs and this one has 2 arcs, then I know these two angles are the same because they're the same amount of arches. Okay, if you see that on the SAT, then they're the same. And now we'll do example questions on that. It'll be pretty easy to recognize. Okay, so basically we know that these two lines, I guess these two lengths are the same. That means this is isosceles triangles. Anytime you see that there's 2 equal angles or 2 equal lengths, then by default, it's an isosceles triangles, which means that 2 angles are going to be the same. So obviously, if you just look at the triangle, you should be able to tell, okay? If I know these 2 lengths are the same, which 2 angles of this triangle should be equal to each other? And you should be able to tell, oh, these two, right? These 2 angles are the same. And that means this one is probably different from these 2, but these 2 are the same. But for isosceles triangles, you just need to know one angle. And you have to be really good at finding it. So all I need is this one measure of any of the angles here, and the fact that it's a isosceles triangle. If I just know one angle on here, then I can find the other 2. Okay, let's do practice. Okay, let's say this was 20 degrees. Okay, we knew this was 20 degrees. And that's it. Find the other angles of this. How would you do it? Because so obviously we already know that this angle is the same as that one. So we know this is also 20 degrees. And we know that all the angles in the triangle add up to 180 degrees. So we can just do 180 minus the 2 angles that we do know. So I guess minus 20 minus 20, so minus 40, right? So that means the last angle here adds up to 140 because 180 minus 40 is 140, right? So we know this angle is 140 degrees. So you see, we just need to one of them. Same thing. Let's say, let's erase this and get new length, I guess new angles. Let's say this one was 100 degrees. Okay, what is the angles of the other two? So this one's a bit harder, but it's also pretty simple. So we know these two angles are the same, right? Because it's isosceles triangles, and we know that all the angles has to add up to 180 degrees. Is the 180 minus 100. So we know these two angles, the angles that are left, has to add up to 80 degrees, because the whole entire thing has to add up to 180, and we subtract 100 from the angles we already know one of them. So these two left has to add up to 80 degrees. Okay. And we know these angles are the same. So you just do 80 divided by 2, which is 40. So we know these are 40. So basically, any time it's isosceles triangles and you know one of the angles, you're able to find the other two. So this is strategy. So if you see a isosceles triangle in the question, you should be thinking to yourself, oh, I just need to find one of these angles that allows me to get the other two. Okay. And the last thing, which is not as common, is equilateral triangles, which I will go over, but this is extremely simple. If you see an equilateral triangle, which is just all the angles and lengths are equal, and again, you don't even need to know, it doesn't need to say itself that all the angles are the same, all the angles are equal. You just need to see like all the lengths are equal. That's enough. Or if you see all the angles are the same, that's enough as well. Basically, you just need one of those two. Okay, and like all the if all the lengths are the same, then by default all the angles are the same. That's the idea behind it. But basically, equilateral triangle. You should already learned this in high school, hopefully. But all the angles of an equilateral triangle are 60 degrees. So if you see an equilateral triangle, then you don't need to know any angles. You don't need to know a single one of them because you already know by default. Like the question doesn't need to tell you what any of the angles are. As long as you know it's an equilateral triangle, you know by default that all the angles are 60 degrees. And just to help you memorize that, obviously all the angles in the triangle has to add up to 180 degrees. And we know all three of these are equal. So just 180 divided by 3 is 60. That's how we know all the angles are 60. So 180, and there's 3 angles, and we know all these angles are the same. So we do 180 divided by 3, that equals 60. So that's how we know that all the angles are 60 for equilateral triangles. Okay, it's basic strategy. See, that wasn't that hard, right? Just to summarize really quickly before we do practice questions. So I'm going to find some pretty hard practice questions. It's just, you need to know these 7 patterns. Okay, these are patterns. I want to think of them as patterns. So if you see like a vertical angle with 2 angles the same, you should automatically think, okay, I can probably use this. And I'll go with strategy when we do practice question. But I think your focus should be around the triangles. Okay, I see a triangle. Oh, I just need to find 2 of the angles to get the other one. But you just look for triangles, and then to get the angles that you need to use these rules, you have to use these. Okay, I'll do example questions just to show you what I mean. So let's look at this question. Hopefully this is big enough. Okay, yeah. So I would pause this video and try to solve it yourself. At least figure out how you're gonna get the answer, and then unpause it to see how I do it. This is just good practice to get yourself feedback loops for checking to see if the way you thought you could solve the question was right or not. Okay. And general strategy wise, obviously I would try to understand the question first. But after I understand the question, I'm going to look at what I need to find. Okay, all the angles I need to find. Like what's the goal? And then try to get triangles around here. You notice there's triangles here. And let me start annotating. So if we see here, there's a big triangle here. Okay, there's a big triangle there and there's a small triangle there. So there's actually 2 triangles in here. We can take advantage of that. Okay, so we know, I don't think it says, let me read the question. I don't think it says that these are isosceles triangles or equilateral. So we know that we need to find at least 2 of the angles here to get the third one. Okay, let me read the question because I don't remember the answer to this or remember how to solve it. This looked hard, so I picked it. Okay, parallel line. So it tells us the parallel line. So immediately you should be thinking, oh, corresponding alternate interior angles. Right, basically just corresponding angles. Okay, you can use that. Q and T are intersected by lines R and S. Okay, got it. If A equals 43, wait, let me get my annotation thing. Okay, so we know these are parallel. Let me just mark that, just so you can follow along with this. So we know these are parallel, and R and S, yeah, these lines intersect the parallel lines. A is 43. Okay. immediately I'm thinking like this big triangle, and this is vertical angles that the one in it. So we already have one of the angles of the triangle basically. Okay, and I'll explain that later. But that's 43. B is 122, and we need to find W. Okay, so we need to find this. All right, we just need to find one of these. But since these are the same, I think we just need to find this one, and then we can divide it by 2 to get like what W is, because we know these are the same. Right, so we need to find this one. How do we get this one? Okay, so again, the strategy is you look at what you need to get and try to make triangles. So here's a big triangle, I'm thinking, because we can probably use this triangle to get this one, right? Because it's supplementary angles, right? 180, 180. Yeah, so if you add up these, they have to add up to 180 supplementary angles. So it's most specifically 180 minus this angle has to equal these two. So you should immediately be thinking, oh, I can use that. Right, so let me finish this triangle here. That's a really bad triangle, but you get the idea. Okay, so we just need to get this angle and then we can get this angle, because that's how a triangle works. We just need 2 of the angles. We already know this angle because we know this is vertical angle to that one. How do we get this angle then? Oh, I see that there are corresponding angles here. And again, this parallel lines, it's pretty much guaranteed you're gonna have to use corresponding angles somewhere. Right, so this is the same as this one. So this is 120 because those are corresponding angles. And look at that, supplementary angles, right? So because there's a supplementary, meaning if there are angles on the same line, these 2 angles have to add 180. So we can just do 180 minus 122 to get this angle. Which quick maths, it's 58. I think, yeah, 180 minus 122 is 58. Sorry, this is a mess. Let me clean this up. Okay. Actually, yeah. Let me just start over. Okay, wait. I'll do this really quick. So we have a triangle, right? And we know we got this was 43 because of vertical angles with angle A, and we got this one is 58. Yeah, because 180 minus 122 should be 58. Okay, so we know these 2 angles. Then we get this one, which is 180 minus these 2. And by the way, like you should be using Desmos for pretty much every question. Let me pull up Desmos so I can just type this in. Because if you're using mental math, first of all, it's slower. Usually, it takes more brain power for you to like think about what the math equals. I would just use Desmos because it's usually faster. It prevents silly mistakes. Just use Desmos every time. So 180 minus 43 minus 58, that's 79. Okay. So we know that this angle is 79. Then we can just get the last 2 because we know this is supplementary angles with these 2, right? Or we just get this one divided by 2. So 180, or you can also do like 180 equals 79 plus like the angle we're trying to find, and then do a regression. If you don't know what I'm talking about, then you should definitely watch my Desmos guide video. But there is a form of this angle plus this angle equals 180, or you could also do 180 minus 79 to get the same answer. It doesn't matter. So we know that this big angle equals 101 degrees. This is 101 degrees. We know these are the same, so we just divide it by 2. Right, so that's just 50.5, right? 101 divided by 2 is just 50.5. So we know then that W equals 50.5. Hopefully that makes sense. And these questions become really easy as you do more of these. But again, the general strategy is get triangles and then take advantage of the triangles. Because you should know, like in your head, like, oh yeah, so I just need to find 2 of the angles. How do I get that? You can work backwards like that. Okay, now let's do another question. Let's do question 18 here. So I would try to pause the video and solve it yourself and then see how I solve it. Okay, so there's 2 isosceles triangles are shown. So right away it tells the isosceles also like does the length. So we know this is the same as that because there's the same amount of slashes for this length. So there's 1 slash, 1 slash. So these are the same. These are 2 slashes, 2 slashes. So these are the same as well. And these 2 lengths are the same and these 2 lengths are the same. If 180 minus z, so that's just the y and z here, because this tells us the relationship. So basically, I'm pretty sure this tells us that if we knew what z is, we can get y. We just use this formula to get y, or vice versa. If we know y, we can get z using this formula. And you can't assume that these are the same, because these aren't vertical angles. Vertical angles is when straight lines intersect each other. Okay, these aren't straight lines. This is a crooked line. This is like that line, right? So those aren't straight lines. You can just tell it's by looking at it. It's pretty obvious. Okay, so you can't use vertical angles, by the way. Y and z aren't the same. So we have to use this formula to get these, and we know y. Okay, so it tells us y, so we can get z immediately, and we need to find x. Okay, that's easy. So isosceles triangles, so we just need to get one of them. We already have one of them, right? It tells us y. We can use that to plug in this formula to get z, and then we can get these two angles and then do supplementary angles with this one to get x. Okay, hopefully that strategy works. So you just take advantage of triangles, basically. That's really the strategy. First look at what you need to find, see how that relates to a triangle. Like this relates to this angle, or how do I get this angle? Oh, I just need one of the, because it's also a triangle, I just need one of the angles and can get the angle by getting that. Okay, it's just a mixture of those. Okay, so so 180 minus, so this was the formula, right? 180 minus z equals equals 2y. Okay, we were given y, I think it said y equals 75. Yeah, y equals 75. Let's just type in 75 here and just see. Okay, so z equals 30 then. And again, if you don't know, this is regression. So like this is, you should learn this. This is Desmos video. It's really simple. It's just how it tells you to estimate the unknown constants, and it's gonna give you what z is. Okay, but I would recommend you watch the Desmos guide if you haven't. So it's 30 degrees. And then we can get the other two here, because we know this one, we can get these two, which is just 180 minus 30, and then the ones that are left would just be these two, and these have to add up to 150, so we just divide 150 by 2 to get what the angles are, so 75. So we know this is 75, then we can, also this one's 75 too, but this one's 75, we just do 180 minus 75 to get the remaining angle. So 180 minus 75, because supplementary angles, right? So that must mean that x equals 105 because of that. Okay, hopefully those questions should seem easy to you now. Like it's pretty simple. Okay, and you can do practice on these all you want to. Okay, now last thing, this isn't one of the 7 patterns. I've only seen one question like this on the history of the digital SAT that required you to know this. But I'm just going to show it just in case. I think it was an experimental question because they asked about it in 2024 and they haven't asked a single question that has to do with this rule again. But this is the rule for the sum of the interior angles of a polygon. Okay, and the formula you have to know for this is 180 times n minus 2. And n is the amount of sides for a polygon. So a polygon is just a shape. Okay, like a polygon is just a shape of sides. Really, and if you've seen the shape, the measures of the inside angles, of the sum of the inside angles. So let me give you an example. So for example, here's like a random shape. Sure. Okay. This is not even straight lines. Okay. But then I drew like a nice looking shape. So the angles of all of these, when you add them up, it should follow this formula. So for this, it has 1, 2, 3, 4, 5, 6 sides. So if we just plug in, n is how many sides, if we just plug in 6 for this, that means all the angles in here should add to 720 degrees. Okay, and by the way, you don't need to memorize this formula because you can just like get it yourself, because we know a triangle, it has 3 sides, there has to be 180 degrees. We know a square has 4 sides and it has to be 360. Hopefully you know a square or like a rectangle has to add up, like the angles have to add to 360. Okay, if you didn't know, now you know. You can just get this formula again, which is the exact same. Like this is the exact same thing as 180 times x minus 2, which is the same thing that we got. Like you see, it's the exact same, right? So you can also just get the angle, get this equation yourself if you forget it. It's like, oh, so yeah, a triangle has added up to this many, a rectangle has added up to this many. We have 2 points on this line. Let's just get the line, and you can just get the equation yourself. Okay. Anyways, enough of that. So this question should be easy for you now because you know the formula, right? So try solving it. Okay, a polygon has exactly 99 sides. So we just plug in 99. Okay. And then what is the sum of the interior angles? This is literally what this number is. Okay, this equation gives you the sum of the interior angles. This is the formula for the sum of the interior angles. So 70,460 is the answer here. Okay, yeah, and this is the formula. You can memorize this if this didn't make sense to you, but I feel like it should make sense to you. Like I would just rewatch that portion until it makes sense to you, because it's annoying to just memorize vague formulas. But if you understand like where the formula comes from and like how to get it, then it's much easier to memorize it. So I would try to like figure out what I did here. So watch the Desmos course, obviously, the Desmos guide, if you haven't done so already, because this would like make a lot more sense what I just did with the regression here. Okay, but that's really it. That's angles, lines, triangles, which is actually a decent part of the SAT, if you look at it. At least in module 1, it's a decent part. Now let's move on to right triangles. For right triangles on the SAT, all you need to know is these 4 rules, which I'll go over one by one. And something that students get confused a lot is these 4 rules only applies to right triangles. You can't use SOHCAHTOA, you can't use Pythagorean theorem on triangles that aren't right triangles. And right triangles are just any triangle that has a right angle in it. Okay, so the question should give away that it's a right triangle because it says it's a right angle or something. So for example, here's a triangle. This symbol usually denotes a right angle. So if you see like a square at the bottom of an angle, like on an angle, that means it's a right triangle. Okay, you can think of like a square or right, like 90-degree angles, right? So right angle. It should say it's like there's a right angle in it, or it should say it's a right triangle, or like you see this square looking thing on one of the angles. Then you know it's a right triangle. If it doesn't do that, then you can't use these 4 at all. Okay, you have to use what we talked about earlier with the isosceles, like scaling, which is you just need to find one angle to get the other 2 angles, things like that. Okay, you only use those. You can't use this stuff. So now let's talk about SOHCAHTOA. So this should be a refresher for most of you, but I'll go over this. Okay, so SOHCAHTOA, what is SOHCAHTOA? So SOHCAHTOA is an acronym. Okay, first of all, you need to know the different trig stuff. So sine, cosine, and tangent. Okay, and better known as SIN, because this is like on the calculator or like on the SAT, you'll see like SIN. So it's SIN of like an angle, let's just use X, and like cosine of an angle and tangent of an angle. Okay, so you see, so this is, if you see cos, tan, or SIN, then that's sine, cosine, tangent. Okay, and SOHCAHTOA is an acronym for how to get these values, or if you have these values, how to get the sides, vice versa, right? So let's just go over this. So sine, is just sine is opposite over hypotenuse. That's what it's saying. Okay, and cosine is adjacent over hypotenuse. And I'll go over this more in depth, but I just want to show you. So tangent is opposite over adjacent. Right, SOHCAHTOA, you can just sound it out. So OH, right? So sine equals opposite over hypotenuse. Okay, what I mean by like opposite adjacent hypotenuse is a right triangle. So let's say we have an angle. It's one of these two. We already know this is 90 degrees. Okay, so let's say we're given one of these. Let's say we're given this angle. Okay, we're given angle X here. Opposite to this angle is this one, right? This is the furthest length, or the furthest side of this triangle from this angle. So that's the opposite angle. This is the adjacent. Adjacent means next to, right? So this side is next to, adjacent to this angle. So that's adjacent. And hypotenuse is just the longest side of the triangle. So whichever the triangle is, it's the one across from the 90-degree angle, by the way. But it's just the side longest from, the longest side in that triangle is the hypotenuse. Okay. So basically what this is telling us is sine, so sine is going to be equal to opposite over hypotenuse. So let's say we're given sine of x. So we're given sine of x. Then, and we were told, let me actually put side so you can like follow along, right? So let me put just like random side lengths for all this. Let's do 3, 4, 5. That's like probably the most common triangle lengths you see. Okay, let's say a question just straight up asked us, what is sine of x? Okay, so what is sine of x? Then we can just do sine, sine SOHCAHTOA, so, right, S-O-H, so sine equals opposite of hypotenuse. The opposite side of this is 4, hypotenuse is 5, so sine equals 4 over 5, opposite over hypotenuse. Okay, that's how you can do this. So all you need to memorize is SOHCAHTOA. So let's do another one. Okay, let's say cosine of x. What is cosine of x? Cosine of x is adjacent, so right? Ka is like cosine equals adjacent over hypotenuse, right? So adjacent, it would be 3. The one next to it is 3, adjacent to it, and hypotenuse is 5, so 3 over 5. Okay, so cosine of x would be 3/5, right? And then tangent of x what is tangent, TOA, T equals O, like O, TOA, right? So you could do 3 opposite, my bad, opposite over adjacent, right? So the opposite to that angle is 4, so and adjacent to that angle is 3. So 4, 3. So tangent of x would be 4, 3. Okay, hopefully this makes sense how you can take advantage of SOHCAHTOA. Hopefully that was just more of a refresher to you. But that should explain what SOHCAHTOA means. You can only use this for right triangle. But it's just like, let's say we need to find this angle, we're given the sides, we can use that. We can just do, oh, this sine of x must equal this, and just have the calculator solve for x for us. Or like, I'll just show you real quick, because I feel like people are going to get confused if I say something and I don't actually do it. So it's like sine of x is equal to 4/5, right? The calculator can find x for us right there. Oh shoot, yeah, the calculator can find x for us. Or let's say it's we're given the angle, and we need to find like what this is, right? Because we know the hypotenuse is 5, but we don't know what the opposite side is. It can do that for us too, like it tells us. Okay, enough of that. Let's just go back here, and let's talk about Pythagorean theorem. Pythagorean theorem is just this formula. It's literally in there. This is the SAT reference sheet, by the way. It's literally in there. So on the SAT testing software, you can press reference on the top right of your screen when you're taking the test, and you can see this picture. Okay, and you can see, oh, c squared equals a squared plus b squared. Just to show you what I mean, let's type in the formula. So again, the reference sheet said c squared equals a squared plus b squared. And let's say we're given a triangle. Okay, and let's do a triangle, a right triangle, by the way. It has to be a right triangle. And like, this is a right triangle because it like told us this, maybe. I don't know. Okay. And we are given 3 and 4. And we need to find what this is. That's easy. It's a right triangle. How do we get, we know 2 sides. It's just like a regular triangle, right? If we know 2 of the angles, we can get the other one. Same thing for a right triangle for sides. If we know 2 of the sides, we can get the third one by using Pythagorean theorem. So, how do we get this? So c squared, by the way, c squared, if you look at the reference sheet, c is the hypotenuse. Okay, c is going to be the hypotenuse. A and b, it doesn't really matter which one you pick, but this is the other sides, the other legs of the triangle, and c is the hypotenuse. Okay, so if we go to our example, if we know a, let me see if I can type. So if we know a, let's say a is 3 and b is 4. It doesn't really matter. It's just like the other sides. And then we can get c, right? Just have decimal solve for c for us. 5. Answer is 5. That's pretty simple. And we could do vice versa. Let's say we know this one, we know 5, but we don't know what this is. How do we get this? Same thing, just use the formula again. Okay, so we just plug in the lengths we do know. We know this is 5. We don't know what this one is. Decimals can solve that for us as well. It's 3. Okay, hopefully that's making sense. Pythagorean theorem is pretty simple. It's literally in the reference sheet too. You technically don't even need to memorize it. Although I would, because like at least you need to know the idea. If I have 2 of the sides, I can get the third one. Let's do a quick practice question just to confirm that you've understood what we talked about so far regarding right triangles. So pause this video, see if you can solve this question, or at least figure out how you're going to solve the question. You don't actually have to solve it, but just like get an idea of how you're going to solve it. And hopefully you did that. So let's do it. So triangle PQR has right angle Q. So right away, I'm confirming myself. Okay, this is a right triangle because it has a right angle in it. Let's draw this out. By the way, you should always draw out anything you can. Like in geometry and trigonometry questions, if you can draw it out, draw it out. Okay, so because you don't want to do it in your head and like mess up the angles in your head. It's not good. It's just like extra few seconds to draw it out. So we know this is the right angle. It doesn't really matter what the other ones are. Let's just like do P and R. Okay, we just know it's a triangle and Q is the right angle. Okay, that's it. So it doesn't matter what these are. Like R could be here, P could be here. Yeah, okay. And then if sine of R equals 4/5, and like we see sine. By the way, the SAT never tests you on law of sine, law of cosine. If you don't know what those are, then don't worry about it because the SAT doesn't test you on them. They don't even test you on trig identities, which you'd probably learn in pre-calc. I take that back. They do test you on trig identities, but you don't need to know them because you can just Desmos them. Like I have seen, I think it might have been an experimental question, but I have seen trig identity questions. Like for example, like sine of something like 30 squared plus like cosine of something square. I don't know, like it's like 80 squared. I know I messed up the square root at different points, but you get the idea. It's like they test you on like questions like this, and then they ask you, "Oh, what is this equal to?" and they give you answer choices. Oh, you just type this in. Look at what it's equal to. I mean, you can convert it. It doesn't matter, but like, you can convert it to degrees if you want to, because it's in degrees or something. Okay, but like you just type it into Desmos, and then just type in the answer choices and see which one's the same. Like you don't need to actually know it. Or if they ask you what is the value of this, just type it in. Desmos tells you. Okay, you don't need to know to get in these. Okay, that's a short sidetrack. You should watch my Desmos guide video if you like want to learn more about just like typing stuff into Desmos, I guess. Okay, so let's solve this question. So by the way, if you see trig, this is a dead giveaway that's a right triangle, because they won't test you. They don't use trig stuff unless it is a right triangle. Like you won't see a trig question involving stuff that's not right triangles. So sine of r equals 4/5. Sine, if we use so katoa, so SOH. So sine equals opposite of hypotenuse. The opposite angle to r is the PQ line here, right, into this length. So we know opposite of hypotenuse. Yeah, so 4. This would be 4. You can just type in 4 here. I'll show you later with like other stuff you can do, because this is a proportion, not really like the exact side lengths. But I'll talk more about that after the question. And hypotenuse is 5. You could do this. Okay. Now, what is the value of tangent of P? So tangent of P, right? Tangent is opposite over adjacent, like TOA, right? So we need to get this over that. The problem is we don't know this, but luckily we just learned the Pythagorean theorem, so we can get this because we know 2 is side lengths. We can use Pythagorean theorem. If you type this into Desmos, it'll be 3, by the way. So if you did 5 squared and then I don't know 4 squared here plus like what you're trying to find, right? It's 3. Okay, so if we know this is 3 basically. Okay, and then we could do opposite. So by using Pythagorean theorem, you can find it's 3, and then you could do opposite over adjacent. So 3/4 is the answer then. Okay, but this works perfectly. I just want you to understand though, like be careful. This is just proportions. Let me erase this. So sure, that's a slightly better delay. Okay, so these are proportions. Okay, 4/5. We just know that this is 4, like for this side over this side equals 4/5. That's all we know. Okay, this could actually, like this side could actually be like 8, for example, not 48, but just 8. Right, and this side could be 10, for example, and then when you do 8 over 10, it's still 4/5, right? Because if you simplify the fraction 8 over 10, it's 4/5. So all we know is that the fraction of this over this equals 4/5. We don't know for sure that this is 4 and this is 5. Hopefully that makes sense. We just know that this is like, if you put this over this, is equals 4/5. Like it could be 8 and 10, for example. It could be like 16 and 20, for example, okay? So I just want you to understand that. But we're fine because this is also proportions, so like proportions don't really matter. But like a way you could just like make sure that you're doing it correctly is, let's say it's a right angle again. This is R. Instead of 4, you put 4x, right? Because it's just like, and then we'll put 5x here, and this just ensures that the proportion is the same. So like anytime as long as 4x, like I don't know what x is, but as long as you multiply like some number to 4 and you multiply the exact same number to 5, if you do 4 times that number over 5 times this number, it's always going to be equal to 4/5, because like the x will cancel out. And like hopefully this isn't overcomplicating it, but I just want you to understand like the nuance of this. Like, this is a proportion, right? It's the proportion of this to this is 4/5. That's what it's saying. It's not saying that this is actually 4. I just want you to understand that in case that causes some complexity. I don't even know how that could cause complexities in the question, but this might like open your mind a bit to just help you better understand trig stuff. But like you could do 4x and then you could just solve for this one, and this would be 3x. And you can literally just type in the exact same thing. I don't know, like 5, instead of doing all this, you could just do 5x, 4x. Oh shoot, sorry, the square is supposed to be after the x. and then some mystery. You don't know what this is, but you know it has to be x something, right? So we don't know if it's actually 3 or not. So let's say like a x, for example, and then you can have Desmos solve for a for you, which you're gonna have to like, yeah, you should watch my Desmos guide if you don't understand what I'm doing, but yeah, it tells you it's 3. So you could do this too if you want to. Like, this is being really nitpicky. Hopefully you understand it. This is a proportion, okay? It's not like saying that's actually 4. Next is special right triangles, and this is also in the reference sheet. It's literally right here. So basically, special right triangles, there's 2 of them. Okay, there's a 30, 60, 90 triangle and a 45, 45, 90 triangle. And when I say 30, 60, 90, I'm referring to the angles of the triangle. So if you have a triangle that has the angles of 30, 60, and 90, then the sides of the triangle should follow this relationship. So basically, if we knew what the side length of the side that's across from the 30-degree angle was, so the 30-degree angle, the side across from that one, if we knew what this one is, then we know that hypotenuse has to be 2 times greater than that length. And the side across from the 60-degree angle has to be that length times square root of 3. Okay, so for example, let's say we knew x was equal to 1. That was 1. Then we know 2x, but if x equals 1, then 2x would be 2, because 2 times x, which is equal to 1, so 2 times 1 equals 2. All right, and if we knew x is 1, then 1 times square root of 3 would just be square root of 3. So we know this is square root of 3. So that if you just know 30, 60, 90 triangle, it's just like the relationship before, right? When we went over the angles, lengths triangles, and where for a regular triangle, you just needed to know 2 of the angles, right? But for a isosceles triangle, you need to know 1 of the angle. It's just like this, okay? So for a regular right triangle, you need to know 2 of the side lengths to get the other one. But for a special right triangle, you just need to know 1 of the side lengths, and you can get the other 2. Hopefully that makes sense. It's just like an isosceles triangle, but it's for side lengths now. I don't know if that helps you. I'm just trying to draw an analogy so you can better understand this. Okay. And a really common pattern for 3069 triangles is if you see a equilateral triangle, right? So again, equilateral triangle is just all the angles are the same. So all the angles are 60 degrees and it's bisected. So like it's cut in half. Then this triangle is a 3069 triangle. This triangle is a 3069 triangle. So if you think about like an equilateral triangle, right? There's 60 degrees on each one, right? So if I cut right down the middle, the 60 degrees turns into 30 degrees. So with this triangle, now this is 30 degrees, it's still 60 degrees, so obviously 30, 60, 90 triangle, right? So this is just a common pattern. If you see equilateral triangle, you cut it right down the middle, that's going to be a 30, 60, 90 triangle. That you see that all the time. Also, a dead giveaway for 30, 60, 90 triangles is anytime you see a square root of 3. If you see a square root of 3 in the answer choices or in the question, anywhere you see a square root of 3, it's like almost guaranteed that you have to use a 30, 60, 90 triangle somewhere. So you see a square root of 3 right there, you probably have to use a 30, 60, 90 triangle somewhere. Okay, so that's a dead giveaway too. It helps speed things up because you can limit down like the amount of things you have to like check to like figure out how to solve the question. You immediately know, oh, I have to use a 30, 60, 90 triangle. Let me just see like where 30, 60, 90 triangle could be and then just go from there. It's much easier that way. Okay, the other special right triangle, which isn't as common but still pretty common, is a 45, 45, 90 triangle. And the most common thing you'll see from this is like, first of all, if you see a square root of 2, like somewhere in the question, that's a pretty dead giveaway that you're gonna have to use a 45, 45, 90 triangle at least like 98% of the time. You see a square root of 2 anywhere in the question. Also, if you see like a square, pretend this is a square, and you cut the square diagonally in half, then what's left is a 45, 45, 90 triangle. So that's pretty cool. It's just like an equilateral triangle you split in half. So you might see this a lot, actually. Yeah, because this is 90 degrees, and this was 90 degrees, but you cut it in half, so now it's 45 degrees. If you also see, another thing that you might see is a isosceles right triangle. Okay, if you hear that or something to do, like it's an isosceles right triangle, or it's like a right triangle with 2 of the side lengths that are the same, then you know automatically it's a 45, 45, 90 triangle. Because what a 45, 45, 90 triangle is just isosceles right triangle. That's it. So like it's a right triangle, 90 degrees, and we know the other side, the other angles are the same because it's isosceles triangle. And so it's by default, these are 45 degrees. So anytime you see a isosceles right triangle, you see a square root of 2, if you see a square that's been cut in half diagonally, it's a 45, 45, 90 triangle. Just want to like help you recognize patterns. Okay, but it's the same idea behind this, right? So if we know like this side, like any of the side, these are the same anyways. But let's say this is 1, then automatically know that this one's 1 as well. And we know the hypotenuse is 1 times square root of 2, because this is s times square root of 2. Okay, it's the same thing as this. Okay, so just need to, for specified triangles, you just need to know one of the sides. So let's practice these. Let's do another example question. So pause this video, see if you can solve this question on your own, or at least figure out how to solve it. Okay, I'm going to solve this question now. So the perimeter of an equilateral triangle, right away I'm thinking 30, 60, 90 triangle. Right, because like, this is just the pattern. If you see equilateral triangle, there's a good chance you have to split in half, and then there's two 30, 60, 90 triangles after you split in half, like I mentioned earlier. It's 624 centimeters. The height of this, yeah, like dead giveaway. So you can see like those patterns on the SAT. You see a square root of 3 equilateral triangle. That should be 30, 60, 90 triangle. So we should make a 30, 60, 90 triangle pretty much. To solve this question, where k is a constant, what is the value of k? Okay, pretty easy. So let's draw it out. Always draw it out, just to make sure there's no silly mistakes. And then equilateral triangle. So 624. Each of that's the perimeter. So all the sides, when you add them up, that equals 624. Since all the sides are equal to each other, we just divide that number by 3 to get each of the sides. So 624 divided by 3 is 208. I wouldn't recommend you do mental math in your head. I would like do Desmos. So I do 624 divided by 3, just to make sure. Because I'm the type of guy that do that. And I actually recommend you do that too. It's like a few seconds. You should already have Desmos, like the calculator pulled up on your screen when you're doing this during the test anyways. Okay. 208. All these are 208. We should split it in half to get the 30, 60, 90 triangle. Because we already know this is 3, so we should probably use the 30, 60, 90 triangle somewhere. Okay. Oh well, that's like sticking out. But okay, so this is going to be a 60-degree angle, because like the equilateral triangle, each of the angles is 60 degrees, and we split this 60 degrees in half, so this is just 30 now. That's the 30, 60, 90 triangle, right? 30, 60, 90. Okay, so 30, 60, 90 triangles, how can we use special triangles for this? You see, let me clear this up. This is on the reference sheet, and 2x, which is what we had, the hypotenuse, right? This the angle, the side across from the 90-degree angle. That's the hypotenuse, right? Hypotenuse. So we know basically 208 is equal to 2x, right? This is equal to 2x. And how do we get x then? We just divided 208 by 2, which is 104. So x is going to be 104, which you could have already gotten, because we already, like, we know this side length is 208, so we bisected, right? We cut it in half to create the 30, 60, 90 triangle, so this should be in half. So it should just be 208 divided by 2. That works too. Okay, but the thing is, we need to find what the height of this triangle is to get k square root of 3. So how do we get the height? Remember, if we know x is 104, the height is just this, right? X, if you look at the side across from the 60-degree angle, that's the height, right? Yeah, 60-degree angle, that's x square root of 3. So this is going to be the height. If we know x is 104, we just multiply it by square root of 3 to get this length, right? So it's just 104 times square root of 3. And if you look at the question, let me erase that portion. If you look at the question, what is k? Like k square root of 3 is the height when you find k. So k is just 104. It's like a number of times square root of 3 is going to be the height. We have the number, we have to multiply by square root. Like this is the number that you multiply square root of 3 by, the 104. Right, so 104, I don't know why you erased it, but you get the idea. So k equals 104. Hopefully that makes sense to you. The last thing you should know to master right triangles is the complementary rule. And you actually don't really need to know the complementary rule. Most of the time, you can just solve any question involving this with Desmos anyways. But I just want you to recognize this pattern in case it does appear and you forgot how to use it with Desmos, or you just don't know how to solve with Desmos. Then I would just like use the complementary rule. Okay, the complementary rule, basically you can recognize this any time you see like 90 minus x. If you see that, that's a dead giveaway. It's a complementary rule question. Basically, the idea behind this is a sine of an angle is equal to cosine of 90 minus that angle. I'm just saying the same thing for the switch around. So cosine of that angle is equal to sine of 90 minus that angle. Okay, you could just memorize this. Again, I'm kind of against like blind memorization. I would like you to understand exactly why where this comes from to help you memorize this better. So I'll just show you real quick. This is actually pretty obvious why this is the case. Okay, here's a right triangle. a right triangle. Let's use the 3, 4, 5 triangle again. So I'm just going to label a side, random side 3, 4, 5. I just want to show you this rule in action. So we know that, let's say this is the 90-degree angle. Okay. Let's say this is x. What would be this angle if this is x? This is 90 minus x. Like, how do we, so if we know two of the angles, we can just 180 minus these two angles to get the rest of them. And since we know this is 90 degrees, 180 minus 90 is 90, right? So these two angles have to add up to 90. If we already have this angle, to get this angle, we just do 90 minus x. Hopefully it makes sense. Like, these two angles have to add to 90 degrees, right? So if you know this angle, you can just 90 minus that angle to get the last angle, right? So that's where the 90 minus x comes from. Sorry, that's a bit, that's a 90 minus x. Okay, now let's do this. So the sine of x, what is sine of x? Okay, sine of x, again, opposite of hypotenuse. Sine of x is 3/5 here, right? That's sine of x, opposite of hypotenuse. What is cosine of 90 minus x? Okay, this angle now, right? 90 minus x, it's adjacent over hypotenuse. That's also 3/5. So this is why this rule is always going to work. Okay, it has to do with right triangles. So basically, this is just like this rule, but in, like, you don't have to think of it, this is like in the formula, right? So same thing for cosine, cosine of x. Cosine of x 4/5, right? Adjacent over hypotenuse. What is sine of 90 minus? So 90 minus x, the one across opposite of it is 4, and the hypotenuse is 5. So it's still 4/5. So you notice, like, this rule works because this is how right triangles work, and like how trigonometry works. But this is just in this form. So anytime you see a 90 minus x, you can immediately know, okay, you probably have to, like, if it asks you what is cosine of x, and that, like, it gives you this, you just, oh, it's literally just the same value. As like it tells you what this equals, you just literally, that's the exact same answer. Okay, so it's just things like that. And I'll show you a quick example question, and I'll also show you like how you can solve questions like that with Desmos. As you just don't overthink it. It's pretty easy. Okay. Oh, it's 4/5. Okay. Anyways, I feel like I've accidentally spoiled this question, but try this question. See if you can solve it. So it says one angle measure x, where x, yeah, so it tells the sine of x, and what is cosine of 90 minus that? So the answer should just be 4/5. Hopefully that makes sense to you. Like, it's literally just the same. Like, sine, if you look at the formula again, sine of x equals cosine 90 minus x. It gave us sine of x, and we know that sine of x has to equal cosine 90 minus x. Obviously, cosine 90 minus x is just the same number. Like, it literally is the same number, right? So the answer is literally just 4/5. Because that's what sine of x equals. Okay, but you can also solve this with Desmos. Actually, so sine of x, right, equals 4/5. We can get what if this is in degrees, you can work with radians too if you want to. It doesn't really matter, but that's in degrees. So we have x, and we can just do cosine of 90 minus x. And we'll get the answer, which is 4/5. Like, you can solve with Desmos too. You don't need to know how to do. Like, I literally just had Desmos solve for x for me, and I just plug it in, and then I got the value. Like, it's pretty simple. This is a standard and just like single variable equation. Like, you watch my Desmos course like on my YouTube video. Like, I'll have it somewhere on the screen every single time I mention it. I just like have it, so you can watch it. You can click on that to watch it if you haven't watched it already for some reason. Okay, but that's right triangles. They're pretty simple. Just remember that these 4 rules can only apply to right triangles. Okay, it's mainly just these two. This is a kind of rare that you'll see this complementary rule, but mainly just these. Okay, and like, you use these a lot. Make sure you know them. You can recognize them. And anytime you see a right triangle, you can pretty much just do a checklist of these 3 things. You can go like, oh, is there SOHCAHTOA? Can I use SOHCAHTOA here somewhere? Oh no, can I use Pythagorean theorem? If no, then it's probably going to be the third one, because it's just like, it has to be one of these 2, or maybe a combination of these 3. But it helps you narrow down what you need to look for. Okay, because you're not like the person that tries everything and spends 5 minutes and still can't figure out what the question is. You know exactly what the SAT is going to test you on. You can just do a checklist to see which one applies. Now let's talk about similar shapes. And if 2 shapes are similar, it just means that they're the exact same, but one of them is bigger than the other one. So the most common similar shape question on the SAT is triangles. They love triangles on the SAT. Okay, but so let me draw 2 triangles just to show you. So if I have these, and if I said these triangles are similar, that would mean that they're the exact same, but one of them is just stretched out more, like bigger. than the other one. For example, if I made like I'm just gonna draw similar shapes for you. So okay, so I said the sides for these is 3, 4, 5, and the sides for this is 6, 8, 10, and these are similar shapes. Okay, you should be able to notice something pretty obvious about these, and it's that every single side of this triangle, and you look at the exact same side on the other triangle, the bigger triangle is always 2 times bigger than the smaller triangle. Right? You multiply by 2 to get from this to this, right? This side, like the leftmost side, right? You multiply by 2 to get there, from this triangle to the other one. Same thing for the bottom. You multiply by 2 from this one to get to this one. Same thing for this one. You multiply by 2 to 5 to get to 10. So it's always multiplying by 2. And this is what similar shapes means. Okay, it doesn't have to be 2, but it's just you have to multiply by the same number from each side to get to the other side. And also similar shapes also share the same proportions as well, but between the shapes, between the sides of the shape themselves. So for example, notice this, if you make a fraction out of this, that's 6/8, which is like this over this, like I guess the two legs of this triangle, 6/8, that equals 3/4, right? And if you do the exact same thing, these two, it makes 3/4 as well. And same thing if I did 10/8, that's going to equal 5/4 as well. So it's similar shapes, basically the exact same shape. Okay, like everything's the same. The only thing that's different is the sides are stretched out more in equal proportion between all the sides. That's what similar shapes means. And just to help you understand this more, squares are always similar shapes. Like if I have 2 squares, they're by default similar shapes. Because a square, the definition of a square is all the sides are the same, like in a 4-sided shape, right? So if I know, pretend that's a square, I know that's actually a rectangle, but then all the sides for this is 1, then if this is a square and I know like all the sides are 2, because it's a square, so all the sides are the same, these are similar. Because if I multiply a number from this to this side length to get to this side length, it's going to be the exact same as multiplying a number from this side length. Like it's going to be the same. Like the scale, it's called the scale factor. Like how big the other shape is compared to the other one. Like the scale, like what number you need to multiply to the small shape to get to the bigger shape. That's the scale factor. Okay, but like there's a consistent scale factor basically between all the sides. So and by the way, it could be 3D as well. It could be cubes. It could be like a rectangular prism. It could be pyramids. It doesn't just have to be 2D. So similar shapes have to have the same proportion between all the sides. And also another way you can prove that shapes are similar is all the angles are the same. Because like the corresponding angles, like the top angle here is the same as this angle. At least like for like any shape, there's at least like a matching angle for every single angle. Like this the exact same. So like this angle is the same as this angle is the same as this angle, this angle is the same as this angle. So all the angles, there's a matching angle on the other shape. That means they're similar as well. So if all the angles are the same, or the sides are proportional, that means they're similar. And we're going to proving triangles in a bit after I go over similar shapes and area and volume questions to help you. Like there'll be questions that ask you to prove similarity as well. Okay, but let's go into like the most common type of similar shape question. And we go to the harder, more unusual ones. Like I mentioned before, the most common type of similar shape question have to do with triangles. And actually, anytime you see more than one triangle, so there's multiple triangles in the question, it's pretty much guaranteed that those triangles will be similar to each other. So anytime you see multiple triangles, it's a similar triangle question. You can just follow the standard process. There's a set 4-step process I use to solve every single similar triangle question. It's pretty much this works every single time. And I'm going to teach it to you. So first, I'm going to solve this question in front of you. And the next question, I'll have you pause it and see if you can use this process for the other question. Okay, but first this question. So a summer camp counselor wants to find length x, right? So just this thing. The length, okay, so this gives us a bunch of lengths, and it says respectively segments, there's like the B, core, okay, E, okay, sure. It says like these two angles have the same measurement, which, by the way, how you read this, because I didn't explain this, AEB, is you just trace it, right? So AEB, so AEB. What angle did that create? It created the angle right there. So that's referring to angle E technically. And like CDB, CDB. So that's talking about this angle. That's how you read that notation. Okay. So the first step of this process is to draw the triangles. Draw the triangles and make them look identical. So what I mean by that is right now, the corresponding angles aren't lined up. Like it's not really clear. I mean, it's kind of like obvious which angles are the same to each other. But you want to draw them out in like a neat format, right? So you can actually like use it. So let's draw out two triangles, make them easily big. It does not have to be perfect at all. Basically, the idea is just to draw two triangles that we can label corresponding angles and sides. Second step is to label the angles, and make sure you don't mess this up. But basically, label the angles that are equal to each other on the same sides of the triangles, right? So we know B is the same because this is vertical angles. This is how like previous knowledge of in this video is going to come into play because it kind of builds off of this. So we learned about vertical angles. I guess like one of the first things it was the first thing we learned about pretty much was vertical angles. So you need to know like how to you have to be comfortable with your lines and angles to solve some of the triangle questions because you want to prove that these angles are actually the same. You can't just assume it is. I think like if you actually said you could just assume because they're pretty much always similar triangles, but it's always good to just like prove for sure that this angle is actually the same as that angle. Or else you get the question wrong. Like I've seen a lot of students like they accidentally think that E is the same as C, and then they line up the angles that way, and then they get the question wrong. They have to make sure they're actually the same. That's actually a really common mistake students make. And also we're told AEB is the same as CDB, so let's put that in. So if this is E, then we know that D is the same as that. You see, it's actually that this triangle is like this triangle, but it's flipped upside down. And a lot of students miss that because they just like, oh, this similar triangle is easy, but they don't actually like take the time to draw it out and label the angles. Okay, that leaves us with A being the same as C, right? Okay, it looks a bit, but you get the idea. Okay, so this is the same. Next step is to label the known sides, like the lengths that we know. All right, so we know the 1800 is the same as AB, so let's do this real quick. So 1800 is AB. 1400 is EB. This was just me reading and understanding the question. 1400. This is telling us which sides are which measures. So 700 is BD 700. And then lastly, CD is 800. So it's 8. That's a really bad. Okay, let me zoom in. 800. Okay. That's not as 0. Oh, well, I tried. So 800. Okay. And what is the value of x? So x is AE. So we need to find this measure, AE. Okay. So what is the last step? Set up the fractions equal to each other and plug the single variable into Desmos. So let's get Desmos. Desmos. Okay. So remember what similar shapes is about. Like, what does similar shapes mean? I want you to see this. It's like not showing up. Okay, there we go. So, what do similar shapes mean? The idea, again, is that all the proportions are the same. Meaning, if I were to multiply a number from 700 to get to this number, which would be 2, right? This is 2 times greater than that. 1400 is 2 times greater than 700. It's the same exact number from this to that. Right? The scale factor is the same. So what I like doing is solving for the scale factor. So what's the scale factor? How big is each side compared to the corresponding side? It's 2 times. But how do you get that? It's just like this side divided by this, like the big side divided by the small side. Right? That's the scale factor. Or you can solve for that. It's like 1400 divided by 700. So like this is how we can solve for it. Like if we had this angle, this side, we could do 1800 divided by that side to get like how many times greater this side is to that side. Okay, this is basic math. How many times greater is the bigger triangle to the smaller triangle? Okay, that's the scale factor. And we just set the scale factors equal to each other because we know the scale factor has to be the same across all the sides. Right, so this side, so because this side over this side equal 2, then that means this side over this side must also equal 2. So we can literally just set this equal, right, this side over this side because we know they're the same. Like the big triangle, the corresponding side of the big triangle over the corresponding side of the small triangle, it should be the same. That's how this works. That's what I mean by setting up fractions. You don't have to cross multiply at all. Just have Desmos solve it for you. Just make the x a constant by putting 1 here and replace the equal sign of a squiggly line. Just the normal stuff. You should definitely watch my Desmos guide if you haven't already. It's like the 5th time mentioning that. Okay, so we know x is 1600 and that's it. You can also do this in your head. Like I understand, like, oh, it's 2 times greater. This one's a pretty easy question, but like this is 2 times greater, so you just do 800 times 2. It's 1600. That works too. Now let's go to a decently harder question, and I want you to solve this question on your own. So pause the video and try solving it. Now there are 2 ways to solve this question. By the way, there's using the area of a triangle. You can use that to solve this question. There's also similar triangles, but I want you to use similar triangles. So the exact process here, this process. Solve it using this process. Okay, hopefully you paused the video and tried solving it. Now, this is actually a really common shape. You see this shape a ton on the SAT, so you should be really comfortable with working with this shape. Basically, it's like one big triangle. Let me just show you what I mean. So this big triangle, and inside a big triangle are two smaller triangles. Okay, if you see this shape, this exact like right triangle, two triangles inside it shape, then okay, you can use similar triangles to solve this question every single time. And notice there's three triangles, so we have to draw three similar triangles. These are all similar, by the way. So let's draw them out. So here's the big triangle. It doesn't really matter, like you don't have to get it perfect at all. But I just want to draw out three triangles. Let's say this is the big triangle. So the right angle is here, right? And these are the right angles. So let's label the right angle. So N is the right angle for the big one. Q is the right angle for the smaller one. So let's label Q and Q. Okay. And let's find the other one. So M, if let's say this is the smallest one, and if we say this is M, then obviously M is going to be the exact same as the big triangle, right? It's literally the exact same angle. So we can say M is the same as the M with the small one. And P, same thing. P is for the medium triangle, the second to smallest triangle. P is the same as the P of the big triangle. So we're going to just say P is the same there. And that leaves us with let me erase this so you can see it better. That leaves us with the angles that are left. All right, so that means that the QPN. So N is left, and this angle N must be equal to this M then. And also this N is left here. Yeah, QMN. Okay, cool. Hopefully that makes sense how I did that. You notice I was making absolute. I'm not just assuming that these angles are the same. I'm actually proving to myself that these are the same because this is literally the exact same as that one. Okay, I can draw that one there. As same as that one, I can draw that one there. So make sure you actually prove to yourself that those angles are the same. Okay, next let's label the known sides. So we know MN it literally tells us right there. MN is 3. So MN, let's say put 3 here. MN is using multiple MNs in this shape. So MN3, NP is 4, NP 4, NP right there, 4. Okay. So we know that, and we need to find the length of N cubed. So we need to find this. Okay, it's also here as well. And this is good enough, right? Because we have 3, 4. We could solve for the other side right there. This is the 3, 4, 5 triangle. I already know. You could do Pythagorean theorem. If you don't know your Pythagorean triplets, I wouldn't worry about it. If you don't know Pythagorean triplets, you don't need it. Just use Pythagorean theorem because the right triangle, we know 2 of the sides. We can use Pythagorean theorem to get the third side. This is 5. Just doing that. Okay, so then we know, okay, 3, 5. So we have enough, right? We could get the scale factor between this triangle and this triangle. Right, this and this. So we just do like 5 over 4, for example, to get the scale factor, and then we just set 3 over x equal to that, because the scale factor should be the same between these two. So let's pull up Desmos and just have Desmos solve that for us. Pretty much no thinking involved. You should get to a point where like, you don't have to think to do this, because it's very standard. Right, so 5 over 4, that's the scale factor, right? And again, so we know that's the scale factor. We can just like use that to solve for the other one, 3 over x. Right, so the answer is 2.4, which is C. Yes, answer choice C, right there. Now, I just want to make sure that you don't accidentally do something like this. Like you don't put like x1 and then 3 here. Okay, it's not how that works. It has to be like if you put the bigger length at the top here, you have to put the bigger length at the top for the other fraction as well. Okay, like the bigger triangles, like this is the big triangle because we used the 5 from the big triangle up in the numerator for this fraction. So for the numerator for this fraction, we have to use the side from the big triangle as well. So don't actually mess this up. And if you weren't able to get these 3, like if you did not notice that there were 3 triangles just from looking at the shape, now you know. And this is pattern recognition. Okay, so it's actually a really common pattern. I need you to learn this. So basically, anytime you see this right triangle shape, and there's it's by the way, this is called the altitude. The height of a triangle is also called the altitude. So if you see the word altitude, which it makes sense, but let me type it out so you can see what I'm talking. How do you spell altitude? I spelled that wrong. I think there's an X with T. I don't know. That might be right. Altitude. Yeah. Okay, altitude. So if you see the word out, if you see this word, that just means the height of a triangle. So if you see, like, for example, there's a right triangle, the altitude of this triangle bisects it by, I don't know what probably not, but like the altitude extends from here to here or something like that. Okay, it's gonna be this shape. So if you see like altitude, if you see like a right triangle, it's just like another right triangle, two right triangles inside that right triangle, like that, it's gonna be this shape. Okay, it's gonna be two triangles. Draw it out like this. You probably have to solve the question exactly how I solved it. Here was a even harder question than the previous two questions, but this is also a similar triangle question. I want you to pause the video, see if you can solve this. At least get an idea of how you can get the answer, and then hopefully you did it by now. Let's try doing this. So in the figure above, tangent B equals 3/4. Tangent B. Well, this has to do with trig, so you need to know like what tangent means, right? So soka towa, right? Tangent is opposite over adjacent, because like towa. That's how that works, right? So 3, so B, this is this 3. At least when you divide this side by this side, it should be equal to 3/4. Like this side divided by this side. And also because like these are similar triangles, these two triangles in here, right? So it's one triangle inside another triangle. These are two triangles, right? The big triangle is a small triangle. So these are similar triangles. They share like this angle, they share this right angle, and then obviously by default that means these angles are the same. So these are similar triangles, right? All the angles are the same. So this also shows the proportion. Like 3, if I divide this by this, it's gonna be 3/4 as well. So that's what tangent is. I guess this, like, you could do like x2, like a different number basically. I don't know. Yeah, but like they should be proportional. So if you divide the opposite over the adjacent, it should be 3/4. That's what this means. Okay, it has a proportion basically between the two legs of the right triangle. If BC equals 15, so we know BC equals 15, and DA equals 40. DA. So it's just this part. Okay, interesting. So it's not giving us like a straight length of the triangle. It's giving us a small part. What is the value of DE? We need to find this. So how do we do this question? We do know one of the lengths, and we know that it follows as like 3/4 proportion. So we can probably solve for x. Yeah, we can definitely solve for x because we know, like, we can do Pythagorean theorem even. Because I already know, yeah, like this it should be like standard for this. I think that it's 3, and like I can do it in my head, x equals 3 because I know 3, 4, 5 triangles. But let me show you like how like an average student would do this. Let me pick Desma. So like this, like you can see, it's a lot harder because you have to use like a bunch of different knowledges from what we've talked about so far. Okay, so yeah, sure, I'll deal with that later. Okay, so we know the hypotenuse of this big triangle is 15, right? Okay, and then we know 3x. Sorry, 3x. This is 3x. 3x squared, or like a squared plus b squared equals c squared, right? So if we do 3x, then we just treat that as like a, for example. So a squared, which is just 3x squared, plus b squared, which is just 4x squared, and 4x. So this is b, and I'm squaring this entire thing. Let me make sure to put the 1 there. It can solve for x for us, which is 3. Right, so this is how you can do it. Okay, as long as there's a single variable equation, there's only one variable you need decimals to find, it can solve it for you. You just need to put in one equation. There's only one variable you need decimals to find. It can solve for the missing variable. If there's two variables, then it's probably not enough. You probably need two equations for that. But like we've got in a situation where there's one equation, there's only one variable decimals needs to find. So obviously you can solve for that variable for us. Okay. That actually comes into play a lot for area and volume questions, which we'll talk about in a bit. So we know x, at least we know x1, like this x, which is 3. So then we can get this side length, right? 3 times 4 is 12. So we know this entire side length is 12. And then we can subtract it from 4 to get like this BD, right? So 12 minus 4, which is just 8. Okay, and let me get what the heck happened to my... Oh, there we go. I delete everything. Okay, so we know this is 8, right? Because we knew x was 3. We did 3 times 4 to get this one, which is 12, minus the 4 here to get what's like this, just this side length. That's 8. Okay. So we know the proportions between these two sides. So like if this is 12 and this smaller triangle is 8, then we have the scale factor already. We can probably use that to get this, right? Because we know, again, this one was 3x. Yeah, 3x. This is 4. Yeah, 4 times 12 to get 12. Yeah, 4 times 3 to get 12. And this is 3x. So 3 times 3 to get 9, because x equals 3, right? So this side equals 9. Let's put that as big side equals 9. So we have enough. Like we just do get the scale factor, like this over this equals this over this. Let's just do that. Okay. So 12 over 8 is equal to 9 over x. And the answer is 6 then. That's what DE equals. Right. Hopefully that makes sense. And like basically sometimes there's questions that give you the proportion, and then you have to use the proportion to get the side lengths. And for this question, I didn't draw out the triangles like this. I mean, I could have, but it's already drawn out for me. Like it's not like it's disorientated like the previous questions. The previous questions were very disorientated. I mean, like it's like this one's flipped around. This is like this is definitely flipped around. But for this triangle, it's already like the corresponding sides and angles already lined up for us. So that's why I didn't redraw. You could have redrawn it if you want to, but I didn't. I just like found the known sides and then used the proportion to solve this question. Let's take this up a notch and talk about a more advanced type of similar shaped question. But these types of questions won't be hard for you because you'll know something that I like to call the proportion trick. So what is the proportion trick? Okay, I'm going to use squares because they're similar shapes, as I said earlier. Basically, you can only do this if they're similar shapes. Okay, like the question should say they're similar, or the question will like give away that it's similar because it says like the proportion between the sides are the same or something like that. That's just what similar shapes mean. Okay, so let's first talk about finding the scale factor. Let's say this was 4 and this was 2. They're just squares, right? But so all the sides are the same. So like this is all 4. This is all 4s, and then this is all 2s. So what is the scale factor between these two shapes? And again, the scale factor is what you multiply to the small shape to get to the big shape. Okay, so what do you need to multiply to like this 2 to get to the corresponding side of the bigger square? Okay, how you get that is you just divide the big by the small, right? So the corresponding side, you take the bigger one, so 4, and you divide it by the smaller one, so 2. So the scale factor is 2. Okay, so because you multiply 2 to the small side length to get to the big side length. Okay, so that's the scale factor. Now, what about the scale factor of the area? Because that's pretty simple, like the scale factor of the sides. What about areas? If all you know is this number, right? We just know that the scale factor of the side length is 2. How do you get the scale factor of the area? Because it's actually not the same number. Let's say the area I already know this is 4. The area of this is 16. You notice if I do 16 divided by 4, the scale factor is actually 4, right? At least when you do areas, right? When you like, what is the scale factor? So what would I had to multiply the area of the small square to get to the big square? It's multiplied by 4 because 16 divided by 4 is 4. So you notice it's actually a different scale factor. Okay, let's try something else. Okay, instead of doing 2 and 4, actually let me just erase everything and just redraw it. Okay, let me do because I want you to like properly understand this. I think this is like a good way to understand it. Okay, let's do another thing. But now let's do like 3 and 9. Okay, so we know all the things. So that means this area is 9 because 3 times 3 because they're squares, right? 3 times 3 is 9. 9 times 9. This is going to be 81 then. And 9 times 9 is 80. I messed up. 81. Okay. So what is the scale factor of the sides? 9 divided by 3, it's 3, right? So you multiply 3 to this side to get to this side. Scale factor is 3. What is the scale factor of the areas? What do you need to multiply to 9 to get to 81? It's 9, right? 81 divided by 9. 81 divided by 9 is 9. So you need to multiply the area. So when you're going from the scale factor of the sides, it's 3. The scale factor is 3. But the scale factor of the area is actually 9. So hopefully you're seeing a pattern. So before, when the scale factor was 2, the area scale factor was 4. Now, when the scale factor is 3, the area scale factor is 9. So you notice the area's scale factor is always the side scale factor squared. Hope that makes sense. So remember, the scale factor of the sides before was 2. If you square 2, that equals 4, right? 2 squared is 4. Same thing for this. When the scale factor of the sides is 3, to get to the scale factor of the area, you square the scale factor of the sides. So let's say all we knew, okay, we didn't know any of the side names of of these square, I guess you could figure it out. But let's say there were rectangles, okay? There were two rectangles. There's two rectangles. Okay, so we just know the question says they're similar, but we don't know the side lengths. All we know about this is that the proportion of the sides to the scale factor is 5. That's all we know. And also we know that the area of this rectangle is 10. Okay, we know the area of the small rectangle is 10. We know these are similar, and that the scale factor of the sides is 5. Okay, how do we get the area of the big rectangle? So since we know the scale factor of the sides is 5, we can just square that number. And then we know, okay, the scale factor of the area should be 25. That means if you multiply the smaller area by 25, you get the bigger area. So this is the area of this bigger rectangle should be 250. Hopefully that's making sense, okay? So if you know the scale factor of the sides, you can square that scale factor, or that proportion, I guess, the ratio, you can square that to get to the ratio or the scale factor of the areas. Now, if you're working with 3D, so not just 2D, but like volumes, okay, not area, but volumes, we're working with volumes. Let's say these are rectangular prisms. And we knew that the scale factor of the sides was still 5. But let me erase this one. All right, so this is actually going to change a bit. So we know the scale factor of the sides is 5, okay? But now we're doing volumes and not, sorry, I need to change this up. Okay, so now we're doing 3D shapes, so we're doing with volumes, not area anymore. And we know the volume of this rectangular prism is 10. What is the volume of this one? Okay, we know the scale factor is 5, and we know these are proportional. I didn't teach you this, so you shouldn't have been able to answer, but if you already know this, then I guess you could. We might have been able to guess this, okay? Instead of squaring the scale factor of the side, you cube it. Now you cube it. So 5 cubed is 125, right? 5 times 5 is 25. 25 times 5 is 125. So we know the scale factor of the volume is 125, and then we do 10 times 125, which is just 1,250. And that's going to be just 125 times 10, right? That's going to be the volume of the big rectangle, a rectangular prism. Okay, that makes sense. So, okay, so from the scale factor of the sides, you square that scale factor to get the scale factor of the areas. So you're going from area to area. If you're going from volume to volume, then you have to cube that scale factor of the sides. It has to be the side. You can't cube the scale factor of the area, okay? Don't get that confused. You have to get the scale factor of the sides, okay? The one-dimensional scale factor, and then you can go to 3-dimensional by cubing it, when you go to the 2-dimensional by squaring it. Okay, I went pretty in depth into that, so hopefully that's going to stick with you, and you'll remember that. Because it makes really hard questions super easy if you just know that trick. Because most people don't know that trick, and you'll be way ahead of everyone that does. I mean, we'll be way ahead of everyone that doesn't know that trick. Okay, let's try this question. This is going to be on the easier side, and I'll slowly make this question harder as we go on. So pause the video, see if you can solve this question. Okay, let's do this real quick. So the side length of square ABCD is twice the side length of square. So right away, similar shapes are squares, right? And it's twice. So we know the scale factor of the sides is 2 because it's twice the side length. Okay, let me draw this out because I should. Right, so here's a square. I know it doesn't look like a square, but we do our best. This is A, B, C, D. I'm just gonna, A, B, C, D. Let's really quickly. And then this is E, F, E, F, G, H, G, H. Okay. Yeah, why are E so annoying as well? Okay. Anyways, this is twice the side. So it doesn't actually tell us any of the side lengths, but it tells us the scale factor directly. Because we know this times, is twice. So actually this one's the bigger one, right? So we get from this, multiply the side length by 2 for this to get the side length of the big one. Right, so this is the smaller one, this is the big one. If the area of square EFGH, so we're given the area, 9. What is the area of square ABCD? So how do we solve this question? It's simple, right? We know the proportions, just like what we did before, right? We know the scale factor, the proportion between this is 9. I'm just making sure. Okay, we know the proportion between the two squares, right, of the sides. So if we want to go from the proportion between the sides, the proportion between the areas, we square it. We square the proportion. So now let's square the scale factors. Now we go 2 squared, which is 4. So we know the proportion between the areas is 4. So then we can do, okay, what is the proportion, what is the area of the big one? We just go from the small one, multiply it by 4. So 9 times 4 is 36. Okay, the area of the big square is going to be 36. That should be pretty simple. Now let's do a harder question. Okay, I'm going to make this question a lot harder. Now instead of the side length of square ABCD, let's do the side length of cube. I'm just going to say, I'm going to keep it ABC, but you get the idea. It's like a cube, right? It's twice the side lengths of cube EFGH, okay? And if let's do the volume. If the volume of square of cube this is 9, what is the volume of cube this? Okay, it's the exact same thing, but now we're dealing with three-dimensional volume instead of area. So what do you do to solve this? Okay, this should be pretty similar in at least how you solve this question. Okay, but you just have to do one thing differently. And this should be pretty obvious. Okay, so the answer is you just, instead of squaring the 9, you cube the 9, right? Because now instead of 2D, we're working with three-dimensional. So I'm sorry if this is like a bit too slow, but I'm like building up to a point, okay? So let's say this was, this is the smaller one. Let's say the smaller one is 9. So we know the proportion between the sides is 2. We cube this now to go from the side proportion or the side scale factor to the volume scale factor. 2 cubed is 8. So we just do 9 times 8, 72. Right, so the volume of the big cube is 72. Okay, now let's change up the question even more, and this is where it starts getting hard. Let's do surface area. Okay, so instead of volume, okay, it tells us the surface area instead. So it says if the surface area of cube this is 9, what is the surface area of the other cube? Okay, so we know the surface area of this is 9. What is the surface area of this? Now, the answer is the exact same thing as we did previously with the area. Like this is just area. So we know if we know the sides of the proportion is 2, we just square it and then we solve it like it's any other area question. So it's 4, right? The proportion between the areas is 4 because we squared the 2. So now the surface area of this cube is going to be 4 times 9, 36. Okay, I think a lot of you, at least, probably not most of you, but a lot of you would have like multiplied it by 6 or something because you think, oh, there's 6 sides and you multiply it by 6. That doesn't matter, okay? As long as it's area, it's a surface area. There might be a surface area, but it's still area. So it's still two-dimensional. As long as it's two-dimensional, then all we do is just square the proportion of the sides. That's it. Okay? And we don't deal with area. If we're doing volume, then we cube it. Okay, so this is just, even if it's surface area, it's still area. So you just square it. Square the proportion to get the proportion between the surface areas. Okay, now let's change up the question even more and make it even harder. Let's say the side lengths. So instead of side lengths, let's do the. I'm going to change this back into volume. Actually, let's do this. So the volume of cube. What is the volume of this? But instead of side lengths, I'm going to say the surface area of cube ABCD is twice the surface area of EFG. Instead of twice, I'm going to do is 25 times the surface area. Just change up the numbers a bit. Okay, see if you can solve this question now. So I changed up the question a decent bit. Hopefully it's still okay. I know it says like cube, but it's not a cube, but you get the idea, okay? Try solving this now. Okay, hopefully you had a chance to try to figure this out. And this is probably as hard as a proportion trick can get. As long as you understand this, you'll be fine. So the surface area of cube ABCD is 25 times. So it's just saying the area of the big one is 25 times the area of the small one. Okay, so that's the proportion between the areas. Right, and the volume, so we know this is 9. And we need to get the volume of the big one. So we just need to figure out what the scale factor is between the volumes. Like, what do you need to multiply to this to get to this one? The problem is, I think a lot of you might have just like squared the 25 for some reason. That is not how you do this, okay? Remember, how do we get the scale factor of the volume? We have to cube the scale factor of the sides. Okay, the scale factor of the sides, that's what we have to cube. So we need to get the scale factor of the sides, basically. How do we get the scale factor of the sides? we need to go from, because we know the scale factor of the area, and we know the area is 25. I use the scale factor is, and we know that this is equal to the side square factor squared. I'm just gonna do S for the side scale factor. Okay, so we know 25 is equal to the side square factor the squared is equal to that squared. So we just need to square root the 25. That way it's going to give us the side of the scale factor of the sides, right? So we can just do 25 square rooted, which is just 5. So then we know, okay, the sides scale factor is 5. And then we can cube the side scale factor to get the volume scale factor. So 5, again, so we need to go back down to the sides. We only work between the scale factor of the sides to get to the volume and to the area. So now that we know scale factor of the sides, we can cube it now. Now 5 cubed is 125. And now we know the scale factor of the volumes, and we do 9 times 125 to get this number, which I don't even know what 125 times 9 is. My brain is not fast enough to do that. Actually, it probably is, but I'm too lazy to do it. So I'm just going to do Desmos. So 125 times 9, 1,125. Okay, that's the answer. That's going to be the volume of the big one. Okay, hopefully that made sense. And if that made sense to you, you'll pretty much mastered similar shape questions. This is as hard as it can get, I think. There's a missing segment here. Okay, we get the idea. Hopefully that makes sense. And if that didn't make sense, I would replay this last part. I was just making sure, because I've seen, like, they have been asking a lot of similar shit. There's been like one every other test. So there's a decent chance you'll see questions like this. And you should definitely understand similar triangle questions as well, because those are super common, like very common actually. They're pretty much always at least one of them every single test. So make sure you know how to deal with similar triangles, and also like scale factors, and be comfortable working with like the volume and the area, and like how to convert between the two, and also like going from side length to volume, things like that. Next, let's go over area and volume questions, which is actually the most common type of question in geometry and trig. So it's pretty important that you get good at this. Luckily, there is a SAT reference sheet that you get access to during test that pretty much gives you all the formulas you need to know for area and volume. Now, however, I would recommend you actually understand where these formulas come from, at least for the simple shape. You don't need to memorize like where the circle, I don't even know, like I kind of know, but like where does pi r squared or 2 pi r come from? I don't think you need to memorize that, but I would like you to memorize, it's not memorize, but like understand where length times width comes from, where length times width times height comes from, where like this formula comes from, okay? So to help you understand this, what is a rectangle? A rectangle really is just a bunch of lines stacked on top of each other. If you really think about it, like we just take one length of a rectangle and we just stack it on top of each other until it becomes a rectangle. Like we just stack a bunch of lengths on top of each other. And how many lengths do we stack on top of each other to get this size of a rectangle? We stack width amount of lengths. Okay, you see like how many lengths we just stack, how many, like however long it takes for you to reach the width amount of the width, right? Like whatever this number is, whatever it's like this measure of distance is. So that's where length times width comes from. It's just, here's the length, and how many lengths are there? There's width amount of lengths. So this is length times width. That's where the area of a rectangle comes from. Same thing, like you can go this way too, like I guess vertically, right? But I guess we're going horizontally this way now. But basically, like how many widths are there? There's length amount of widths. You really just like line up the widths side by side until you get a rectangle, and then how big the rectangle is just like how many widths you stack next to each other, which is just the length. Okay, that's where length times width comes from. Similarly, if you look at a rectangular prism is really just a rectangle, like the base of this, like the rectangle, but you stack up a bunch of different rectangles. Like here's another rectangle, here's another rectangle. You just keep on stacking up rectangles until you have a 3D shape of a rectangular prism. And that's where this comes from. So it's actually just the base of this rectangle with length times width, right? Length times width is just this rectangle. So the bottom rectangle, and you just keep on stacking on top of it. How many times do you stack up rectangles to get a rectangular prism? It's height amount of rectangles. So that's why it's actually the base times the height. And this is why I want you to conceptually understand this, because the question might not give you the length, the width, and the height. Instead, the question might give you the base of a rectangle and ask you to get the volume. And it gives you the height as well. So it gives you the base and the height. Then you know, oh, it's just base times height. You don't need to know length times width times height. But you know, oh, length times width is the base. So you can actually like solve questions even though it doesn't give you exactly what the formula tells you. So it's kind of important that you actually understand where everything comes from. Same thing for the volume of a cylinder. If you think about it, pi r squared, that's just the area of a circle. Pi r squared, right? This is this area of the bottom circle here, right? Pretend like the base of the circle. It's exactly the same as a rectangular prism. Okay, like to get a cylinder, you just stack a bunch of circles on top of each other. It's like this entire area of the circle, you just stack on top of each other until you reach height amount of circles stacked on top of each other. And that's why it's the base of the circle at the bottom, right? The area of the circle times the height. This is the circle and you stack on top of each other until you get the height. Now, having a conceptual understanding of where these formulas come from is also super helpful for finding the surface area. Because the SAT loves asking about the surface area. I think it's because it's like a hard thing to do and it's not a formula already in here. So they want you to like conceptually understand where formulas come from, or at least how surface area works. So the only shapes I think you need to know how to find surface area of is the rectangular prism, the cylinder, as well as the pyramid. And this could be a triangular pyramid or a rectangular pyramid, which I'll talk about once we do a practice question for pyramid. But for now, let's go over how to get the surface area of these. So surface area is just the sides of the areas of all the surfaces added together, right? So for I guess a cube or a rectangular prism, there are 6 sides, right? I'm trying to draw the sides that you know. So the bottom side, the back side, the top. So there's 6 sides, right? You imagine a rectangular prism, a box. There's 6 sides. You just need to individually get the area of each of the sides and add all of them together. That should be pretty self-explanatory. Now, how do we get the surface area of a cylinder? Okay, if you think about this is why it's helpful to understand like where the volume formula comes from as well. If you think about it, first of all, we can just get the area of the circle up here and the area of the circle at the bottom there, which should be the same. So we can just do pi r squared times 2, right? That's going to give us the areas of the circles on top and bottom. But how do we get like the side, right? The area of the side? How we do that, it's actually pretty simple. Because if you think about it, how we got the volume in the first place was we just took the area, we just stacked a bunch of circles on top of each other, height amount of times until we got to the entire cylinder, right? How we can get the surface area, at least like the area of this like round part of the side, we just get the circumference, which is just the hollowed, so it's just the perimeter of a circle, the circumference, right? It's the perimeter of a circle. So if we just get like a hollow circle, like nothing's inside, like a hollow circle, and then we just stack up the hollows like hula hoop, I guess, on top of each other over and over again, that's going to be a cylinder. Right? It's going to build us a cylinder. We just stack a bunch of like hollowed out circles on top of each other each amount of times. That'll give us this area. So it's really just the circumference times h. Okay, if that didn't make sense to you at all, you can also think about this as a paper, as like a piece of paper that's rolled up, and then you like unroll the piece of paper. What shape would that turn into? So imagine this is just like a rolled up piece of paper and you unroll it. What's the shape? It should be a rectangle, right? And rectangle is just length times width to get the area of that. And the length should just be the circumference. Because if you think about it, if you roll out the paper, you're just rolling out the circumference, right? The perimeter of the circle, you're just rolling this part out. So that's just going to end up being the length of this new rolled out rectangle. And obviously the height's going to be the width. So it's just length times width, which is just the circumference times the height. So basically, the formula for a surface area of a cylinder is simply just the pi r squared, which is just the area of the circles. There's 2 of them, so 2 times pi r squared, plus the area of the side part of the cylinder, which is just the circumference times the height. And again, I don't even think you should memorize this. I don't have this formula memorized, actually. But I do know how to get the formula because I conceptually understand how area and volume works, and I'm able to just remember this. Like I don't need to think about it. I can just like do it because I already understand how it works. Okay, hopefully that makes sense. And you don't need to memorize the surface area for any other shapes other than I think the rectangular cylinder in a pyramid. You need to know how to find that too. It's not really memorization. You just need to understand where it comes from. But if they ask you for like a surface area of a sphere, they'll give it to you. Okay, that's a crazy shape. I don't even know the surface area of a sphere. But just make sure you know these 3 shapes. Okay, and we'll go over the pyramid in a bit. It's actually a bit harder than you think it is if you don't have experience with that. But first of all, let's just jump straight into a question. So see if you can solve this question. Okay, hopefully you pause the video and try solving it. Let me make my head a bit bigger. So a general strategy for area and volume questions is just to get the formula of the area and or the volume, or if there's both in this case, and get the formula for both of them, which should be pretty obvious, but it helps you like simplify the situation. Okay, so there's always going to be like an area of volume because the area of volume question. So just get the formula of that area or get the formula of the volume or both, and then just go from there. It's going to be really easy as long as you do that. Okay, so surface area, the cube has a surface area of 54. What is the volume? So you notice in the reference sheet, it doesn't actually tell us that the volume of a cube is this. It doesn't say that. However, a cube is just a rectangular prism with the length, width, and height being the same measure. So it's just length times width times height. But the length, width, and height are the same number. So it's just the same number multiplied to itself 3 times over, which is just that number cubed. Right? So that's actually where the like why it's called cubed. At least I think that's why it's called cubed. At least I hope so. Because like the volume of a cube is just one of the side lengths cubed. Okay, that's the volume of a cube. And this is also why like you want to understand it conceptually where the formulas come from. Because I've had students actually get stuck on that because they're like, oh, it doesn't tell me what the volume of a cube is. How do I figure that out? Oh, you just have to conceptually understand it to figure that out. Okay, and the surface area of a cube. Now this is slightly harder. So imagine the cube. There's 6 sides. All the sides are the same. You get the area of each of the sides, and there's 6 of them, and they're the same measure. So we just get the area of one of the sides multiplied by 6, and then get the surface area, right? So the area of one of the sides is go figure start thinking squares because the area of a square is just going to be a side length squared, and that's why it's called squared. I don't know if that helps you memorize it or not. I don't know. Okay, but that's the formula. So it's just one area multiplied by 6 because there's 6 sides, surface area. And then we can just solve it now. So like again, the strategy was just to get I mean, this one's a pretty easy question, right? And you'll see a harder question later on, but you get the idea. It's just get the volume and the area, or the formulas for those, and then you can go from there. And we can just solve. I'm going to use regression, turn into a constant. Let's solve. Actually, we need to know. Wait, hold up. We need to know what this is first. Okay, and then okay, so we know x equals 3. So the side length of this cube equals 3, and now we can plug in 3 into here to get the volume 27. So the answer is B for this question. Okay, now let's go to a much harder question. Good luck on this. See if you can solve it. So pause the video. Try solving this question. Okay, hopefully you tried at least like figured out a direction to go to solve this question. Okay, so figure shown is a right rectangular pyramid. So there's actually 2 types of pyramids I've seen on the SAT. There's a rectangular pyramid, and I've seen triangular pyramid as well. This might say triangular. And basically what that's saying is just the base. Okay, a rectangular pyramid is saying that the base of this pyramid is a rectangle. That's why it's called rectangular pyramid. If it's a triangular pyramid, then the base of this pyramid is just a triangle. Okay. There's not really anything special about it. It's just like, remember you're getting the area of this triangle instead of rectangle. Right? You remember to divide it by 2 or something. But like hopefully, like sometimes they might not give you the picture. So like when you're drawing it out, you know if it's a triangular pyramid, and it's actually the base of this is actually a triangle, not a rectangle. Okay, and this right thing, you can just ignore this. This right, it might say right cylinder, right triangular pyramid, right rectangular pyramid. That's just, I think that's just referring to the fact that there's a right angle. Like it's just like a straight up, like it's just a normal shape, right? It's not like a slanted pyramid or anything. Okay, so it's just like if you drew a line straight down from the tip to the base, it's going to form a right angle, and that's what it means by right. You can just kind of ignore that because they never test you on things that aren't right pyramids or right cylinders. You can just kind of ignore this. But really, like rectangular and triangular, that kind of matters. So this is the rectangular pyramid. You guys label the known size. So length is 18. The width is 9. The height is 12. Okay. So got it. So how do we, like, so I think we can easily get the area of this rectangle, right? Length times width. Let's actually put that. So again, we just try to piece together the formula. Right, so surface area is just all the areas of the surfaces added together. So we can get length times width, which is just what it's 18 times 9, right? 18 times 9, length times width. Okay, so this we'll get the area. So surface area, because we do SA. So surface area equals this. Now we need the different sides, right? This side, the area of this side, I guess the area of this surface. Okay, and there's going to be like this surface is going to be the same as this surface, right? And like this surface is going to be the same as like the surface that we can't see, right? So as I guess we could do like surface like 2 times, I'm going to call this like surface A, like this one, the one that's facing us the most, surface A, and then this one surface B, I guess. So this is 2 times A plus 2 times B, and we need to find like A and B. Okay, hopefully I'm not confusing you with all these different things. Hopefully this makes sense. So, right, we just need to get, this is the exact same as the base one. So that's why so I just need to find, like, I call this A, so we just get the area of this multiplied by 2. This is what I mean by like getting the formula. This helps you break it down. Okay, so how do we get A? Now, I think most of you, like, to get this formula, the area of this surface, a lot of you, I'm not sure if most of you did, but a lot of you will just do like height times the length, right? Because you think, oh, the area of a triangle is the base times the height divided by 2, right? So you did like the height, like this height and this length, which is the base. That is incorrect. Okay, you would get the wrong answer. It's very incorrect. And this is a common trap people fall into. If you have a pyramid, okay, that's this height from the tip of the pyramid to the base, like the height that's shown here, the height of the pyramid is a different number than the slant height, right? Like this diagonal thing, like the height of the triangle, like that of the side we're facing, right? This height of the triangle is a different measure than the height of the entire pyramid. It's not on the same dimension. Okay, so you have to actually find it. This is called the slant height, the height of the slant of the pyramid. Okay, not the height of the entire pyramid. So how do we actually get the slant height then? How do we get this height? Okay, we can remember there's a right angle here. Like this forms a right angle. There's actually a right triangle right there. That's actually what we get. This is the hypotenuse of a right triangle. So we know the height, right? This was 18. We know the height of this pyramid, it's 18, and we know this as well because this is just half of the length, which is 18. Right, 18. Sorry, wait, this isn't 18. This is 12. My bad. So the height is 12. Yeah, this is bad. Height is 12. That's the value, and then this is going to be 18. So just half of that, which is just like this leg of the right triangle, that's 9. Then this is half of the length. So basically, we know 2 legs of this right triangle, 12 and 9, we can get the hypotenuse then using Pythagorean theorem. So let's just do that, right? So we know we need to find the hypotenuse, and we know a squared plus b squared, which is just 12 squared plus 9 squared. Let's have Desma solve c for us. So c is 15. Okay, so that's actually this height, I think, yeah. So like the length times the height, if I'm so like this side thing. Okay, so that's the slant height of that. So we know that's 9. So let's just solve for the area of this triangle then. Because we know the slant height now, which was 15 as we found there. And we know the width, which is 9. So base times the height, 9 times 15 divided by 2. So A equals 9 times 15. And remember to divide by 2 because it's a triangle. Now it's times 1/2. Okay. So this is just 9 times 15. So base times the height divided by 2. That's going to be the area of this triangle. Multiply by 2 because there's 2 of these, like this one and the one this side too. Okay, now we need to get this triangle, which is a different measure than these, right? Because they have like a different base for multiplying. Like this one, the base was W. Now the base is the length, and even the slant height is going to be different now, right? Because we don't know. So let's calculate the slant height again. So we use the exact same thing we did before. Let's do that, but the only difference now is it's going to be this. Instead of this length for the leg of the right triangle, it's going to be this length now, which is actually half of the width, not half of the length. So half of the width is 9, so it's just 4.5 then. So instead of 9, we put 4.5, right? That's going to give us the new slant height, because the height's still the same. Like this measure is still the same. It's just this thing that changed. So we put a new number for that. That's going to be the slant height of this side. Okay, so C. It's not a nice number, which kind of scares me, but I'm pretty sure we're doing everything correctly. Like, I'm being really careful with every step we're doing. So that should be the correct answer. Anyways, okay, so 12, so C, let's just type in C. Yeah, sure. C times, actually, I'm not, sure, that's fine. Okay. So C equals that value. We just do C times, C was the height times the base, which is L, so 18. Okay, and then we times 1/2 because it's a triangle. We multiply it by 2 because there's 2 of them. Okay, so now we should have the volume. Sorry, the surface area. Okay, the answer is 527.6 or 0.7. So actually, if you didn't know, on the SAT, you can only type in 5 characters. For numerical response questions where there's no multiple choice and you have to type in the number yourself, it only accepts 5 characters max. You can actually round this number to 7 if you want to. It doesn't matter. You don't have to round it. But it can only accept 5 characters. So basically, it won't even let you type in a 6th character. By the way, a negative sign does not count as a character. So if you put a negative sign, I guess you could type in 6 characters if you want to. But there's no negative, so that doesn't matter. Okay, you just type in 5 characters. Negative sign doesn't count as a character. The decimal point does count as a character. So that's 1, 2, 3, 4, 5. You can type in. You can round this last one if you want to. It'll accept both ways. It doesn't matter. Okay, but it won't even let you type anymore after you type in 5. So you just like keep on typing until you can't type anymore, and then it'll accept that answer. Okay, so the answer for this one was 527.6 or 0.7, depending on if you rounded it or not. Okay, now let's do another question. This question should be simpler in terms of like the amount of steps it takes. Okay, but hopefully like, you can use the same strategy of just, okay, let me get like an idea of what the formula is, and then just like try to like piece together what the formula is, and then you can get the answer. Hopefully, we'll just do this question. It will make more sense as we do more of these practice questions. Okay, hopefully pause the video and try solving it. This says a cylindrical can. All right, there's no diagram, so actually I have to draw it out. Fine, okay. So a cylindrical can containing pieces of fruit is filled to the top with syrup before being sealed. Okay, so basically there's like a cylinder, and the only thing inside the cylinder is fruit and syrup. Okay, so there's a cylinder, there's pieces of fruit. I'm just gonna put dots as fruit. So there's a bunch of fruit, and there's a bunch of syrup inside this. Okay, and there's just fruit and syrup. The base of the can has an area of 75 centimeters squared. So we're given the base. Yeah, this is a great example of the fact that you can't just like blindly memorize these formulas. You have to understand where it comes from, because it just says the base. It doesn't tell us the radius at all. So if you don't have the radius, like how are you supposed to get this? Right, but it tells us the base, and we realize, oh, pi r squared is the base. So this is the base times the height. And I bet he's going to give us the height, right? Let me check. The height of it literally gives us the height. So the formula for the volume of this entire cylinder is actually base times height. Okay, and you wouldn't have realized unless you actually conceptually understood where the formula for this comes from. This is the base times the height. How many bases stacked on top of each other is height amount of bases. At least that's like how it makes sense to me. Okay, hopefully it makes sense to you. So if 110 centimeters cubed of syrup is needed to fill the can to the top, with the volume is closest to the total volume. This is closest. That means we can round. Okay, the answer we get doesn't have to be the exact number. If it doesn't say closest, or it doesn't like hint that we need to round the answer, then if you don't get the exact answer, you got the question wrong. Okay, you have to get the exact answer for multiple choice questions, or you probably made a mistake somewhere. So the following is closest to the total volume pieces. Okay, so let's okay, the basic strategy, right? We just get the equation of the volume, and then we can work from there. So we're trying to find the volume of the pieces of fruit, though. But let's first get the volume of like the big can. Right, we can do that. This is base times height, as we discussed before. This is the base, which is the circle base, and it's how many bases stacked on top of each other. It's 10 centimeters, or the height amount of bases. So it's just base times height. Okay, that equals the volume. Now, how do we do this? So we just need to find the pieces of fruit in the can, and all that's in the can is just syrup and fruit, and we know the syrup. So if we subtract out the syrup, what's left is going to be the fruit. Hopefully that makes sense. Does it make sense, because there's only 2 different things in this that makes up the volume of this entire thing. And if we get rid of all the other stuff, what's left is just going to be the fruit, which is what we're trying to find. And this is actually a really common pattern where you find the area of the volume of the entire thing, you subtract out the unneeded stuff, and what's left is the stuff that you want. For example, they love asking questions with like shaded regions. For example, let's say there's a big rectangle, and then there's like a shaded region in here. So let's do this, and then there's like a shaded region. It asks you for the area of the shaded region. And how you would solve this question is you just get the area of the entire rectangle, and then you just subtract out the area of the small rectangle inside here, and what's left is just going to be a shaded region, right? So it's the same strategy. Well, you trying to find something. There's no exact formula to get it, but what you can do is get the area of the entire thing, subtract out the stuff that you don't want, which is just this mini rectangle here. Then what's left is going to be the thing that you want. So the same idea here. So I want you to recognize that pattern in case you see something like that. That way you don't have to spend time thinking about how to solve the question. If you see this type of pattern where it's like, oh, unneeded stuff, and what's left is the stuff that I want, then you could just use this pattern right away. But this is 640 is the answer. Oh, we didn't even need to like round or anything. It's literally it was the answer right away. Okay, yeah. The answer here was 640, then C. Okay, let's talk about more patterns. So the next pattern is inscribed shapes. And I want you to pause the video and see if you would be able to figure out how to solve this question, at least like have an idea of how you could. Okay, hopefully you like read the question and you tried your best to like figure out how to solve this, because it's going to make this way more memorable. Okay, there's actually a really good strategy for inscribed shapes. Okay, so in the figure, rectangle EFG, so it's just this rectangle, right, is inscribed in a circle C. So basically what inscribed means is just it's as big as it can be inside that other shape. Right? It doesn't even have to be a rectangle inside a circle. It could be the other way around. Let's say there's a square and there's like a circle inside the square. But inscribed shapes is basically meaning they're touching at like the max. Like this circle cannot be any bigger inside the shape. Same thing for this. This rectangle can't be any bigger. At least like proportionally, it can't be any bigger. Right? And it's like all the edges of the rectangle are touching the circle. That's what inscribed means. It could be like a triangle inside a circle. It could be like any shape inside. It could be 3D, like there's a cube inside of a sphere, things like that, okay? But the general strategy for inscribed shapes is you have to find the common length between the two shapes. So what I mean by that is what length can we work with between the two shapes? And that's if we can find what the common length is, there's going to be one length, at least one that's going to be in common between the two shapes, and we can use that length to convert between the two shapes. Okay, so in this case, which has a radius of 10. Okay, so we're given HG, which is this, and we're given the radius of the circle. Okay, but before we deal with that, what is the common length between the circle and this rectangle? Okay, a good strategy to find this common length is to look at the points where they're touching. Okay, if you notice this point, we just draw a line between these points. You notice that's the diameter of a circle. And it's actually really easy when you're dealing with circles to deal with inscribed shapes, because really all you know about a circle is just a radius and a diameter. Like that's the only lengths we can work with. Radius and diameter. Radius is half the circle. Diameter is the length of the entire circle. Like that's all we can work with. So we just see, okay, does the radius or the length match something that we can use in the rectangle? And the radius, I mean, maybe we could use like what length of this is the rectangle? Like how can we use the radius in the rectangle? We can't really. So it must be a diameter then. So if you draw like a diameter, just keep on drawing diameters, you probably realize, oh, the diameter of the circle is the same as the diagonal of the rectangle. And we can use the diagonal of the rectangle, right? So we can convert. So since we have like 10 radius of 10 for the circle, that means the diameter is 20. Okay. So that means the diagonal of this rectangle is going to be 20 as well. And that's how we can convert between the two shapes. So let's say it gives us information about the circle, we can find the common length between the circle and the rectangle to convert from length from a circle to a length to the rectangle. In this case, it was the diameter and the diagonal. Now we can do, okay, 20, so the diagonal is 20 as well. We're also given that this is 16. And what do we need? We need to find what is the area of E. Oh, that's weird. EF, so like this triangle. We need to find the area of that. Okay, yeah, so you notice there's a right triangle there. That's pretty simple, actually. So like this is 20, that's the hypotenuse of the right triangle. And then we can do, here's a triangle, the right triangle. What you can do, because we're trying to find the area of this anyways, it's the same measure, it doesn't matter. But you could just think of it like this, because if this is 16, then this must be 16, because that's how rectangle works, right? It's like these two lengths are the same. So this is 16, this is 20. And then we can just find this missing length. And once we find that missing length, we can just do base times height. Or I guess you could think of it, it depends. Like if you orient the right triangle like this, is base times height, right? So base times height divided by 2, and that would be the area. Because how do we get that? That should be 12, I think. But by the way, if you're curious how I did that, like how I was able to like get the side really quickly in my head, that's just Pythagorean triplets, because I know 3, 4, 5 triplets. If it doesn't make sense to you or isn't familiar, just don't worry about it. You can just do Pythagorean theorem, which is just we set up on this as 20, right? So 20, which is c squared equals a squared plus b squared. Let's say a squared is 16. That's what GH equals, right? It's, yeah, oh, HG, same thing, plus FG, which is, what is called B squared, why not? And we can solve for B squared, which is 12, like I said. So we know the base, or you can do is height, doesn't matter. So base times height, 12 times 16 divided by 2. So 12 times 16 divided by 2. The answer is 96. So C, you would pick. And then that should be the answer. Right, hopefully that makes sense. Inscribed shapes, just find the common length between the two shapes. Okay, because they're inscribed, it should be pretty easy. Just look at the points that are that are touching, and then try to like see if you can like draw common lengths. And if you're doing a circle, try drawing the radii or the diameter and see if that works. And it shows the shape that's inscribed, or like it's being inscribed in. Okay. Next, let's talk about proving triangle questions. And you notice these questions only show up in the hard second module. They don't show up at all in the first module. And I doubt it's going to show up in the easy second module if you get the easy second module. But because these questions are hard. It's just supposed to be hard. They're actually pretty simple if you know what you're doing. But like they're kind of like a niche thing that you just have to know what to do. If you don't know it, then you're going to get the question wrong. But if you do know it, it's pretty simple. Okay, so the proving triangles, the main thing is proving congruency and proving similarity. So I'll go over this. So first of all, what's the difference between congruency? So like proving something, two triangles are congruent to each other and two triangles are similar to each other. Now, congruent just means they're the exact same shape. Like literally the sides are the same, the angles are the same, every single thing about the shapes are the same. Okay, congruent doesn't just apply to triangles, but I've only seen proving triangle questions on the SAT. But it could be like congruent, like rectangles or something. I don't know. I've never seen that though. But you get the idea. It's congruent just means they're the same. And then similar, which we talked about earlier, is just one of them is bigger than the other one. Okay, they have the same angle, like the proportions are the same, but one of them is just bigger than the other one. That's similarity. Okay, so those are the differences between congruency and similarity. It's really important that you know, because a lot of people get those confused. Okay, congruency is they're the same, similar is one of them is bigger than the other one, but everything else is the same. Like the angles are the same and everything. Okay. Now, there's different, I guess, ways you can use to prove if something's congruent and different ways you can use to prove if something's similar. Let's actually go over similar triangles first, because we already went over that earlier in this video, and we could just do a quick refresher. But there's two ways to prove similar triangles. There's only two, by the way. Okay. First way is proving that the angles are the same. Okay, all the corresponding angles are the same. So basically, if you have a triangle, and you have another triangle, and let's say one of the triangles angles equals 30, 60, and 90, and the other triangle also equals 30, 60, and 90, like the angles, then we know those triangles are similar to each other because all the angles are the same. And actually, you just need to know two angles that have to be the same. Right? Because we know, if we know two angles of a triangle, let's say we know one triangle is 30, 60, and we don't know what this one is. Like we don't know what the last angle is for this triangle. And we know the other one is 30 and 60, and we don't know what the last one is. This is enough to prove similarity. Because if you know two angles, you can get the third one. Right? Like 180 minus 30 minus 60, that's going to equal 90, obviously. So we can solve for the other ones. As long as two angles are matching, two separate angles in the triangles are matching, then we know those two triangles are similar. So that's one thing, proving angles are the same. And the other way to prove that triangles are similar is proving that the side lengths of the triangles are proportional to each other. Now, this is different from angles. We can't just do two. We have to do all three of them, actually. So let's just show you. So let's say we know one of the sides of a triangle is 2, one of them is 3, one of them is, I guess, let's see, that's not possible. I'll show you why later on, because you'll learn why that's not possible. I think this is probably possible. But yeah, okay, so 2, 3, and 4. Okay, those are the sides of a triangle. Is that? Yeah, I think it's okay. And then that means and then another triangle was 4, 6, and these are the sides of the triangle again. Okay, so we know one triangle has the side lengths 2, 3, and 4, and the other one has 4, 6, and 8. You notice this one, like if you look at this triangle, there's always a side length that's 2 greater than the one before the smaller triangle, right? So that means it's always like the scale factor of 2, and it's consistent between all the sides. So that means that these triangles are similar. Now, if you only need one, that's not enough. That's not enough. You need to know all of them, because you can have 2 triangles. Like you can have a triangle, and like we know these side lengths, but this third length can be drastically different. Like it doesn't have to be the exact same triangle. Like it could be this side length, or we can take the exact same lengths, like this length, and make them, like, for example, this and this. And like this third length would be drastically different. Right? It's like, imagine this is the same as this. So basically I'm just showing you that just knowing 2 of the sides of a triangle doesn't automatically determine what the third one is. Because we don't know. That's only for right triangles where you can use the Pythagorean theorem to get the third one. This is just regular triangles. So just knowing 2 of the sides isn't enough. You need all 3 of the sides to actually prove that, oh, all of these are proportional. So it's much easier to prove with angles. But sometimes the question like forces you to prove using the sides and show that they're all proportional too. But that's how you prove similarity. Okay, so there are 2 ways. Okay, don't get us confused with congruent triangles. My bad. It's only for similar triangles where you can use all the angles are the same, or I guess 2 of the angles are the same, and or all the sides are proportional to each other. So actually, let's solve this question. See if you can do this. This is on the harder side, by the way. So read really carefully and try your best. So pause this video, see if you can do this. In triangles LMN and RST, angles L and R each have measured 60. So let me draw this out real quick. So LMN. I'm just drawing regular triangles because it doesn't say that they're right triangles. This is R. That's a really small R. Oh well, ST. Okay, we know L and R. So I'm not gonna like actually write out. This is why I usually like to. I just like symbolizing to myself. Okay, these are the same, right? And LN 10 or T30. LN. I know they're not the same length, and this notation means they're the same length. But I'm just like doing this is to show. Okay, we know these. And by the way, I'm thinking this isn't enough because it doesn't tell us any other stuff about the side length. We do know that there's like a scale factor of 3 here, right? Like this is 3 times greater than this. The problem is we need all the side lengths to be like that. Like this has to be 3 times greater than this. This has to be 3 times greater than this. So we need like 2 more pairs of side lengths. But I don't see that. I only see like 1 more pair. So right away you eliminate A because this should be 3 times greater than this one. This is the same. That's not good. Okay, we need to be consistent. Right? Since this is 3 times greater, we need to have the same proportion between the sides. This one is 3 times greater, but it's like NN and ST. That's not good enough. We need all 3 of them. Again, just knowing 2 of them doesn't automatically mean that the third one is proportional. So we can eliminate B. So it has to be C or D. Now let's read C. The measure of angle M and S are 70. So it says this. No, they have to be the same. These are corresponding angles, right? If we drew so these have to be the same. And it says the difference. So that's wrong. It might be that like S is supposed to be this angle. We can work that out. So I'll show you what I mean. So like the measure of angles M and T are 70 and 50. So if we draw this out again, because it went away, it said M and T. Right, so this is LMN and this is RST. So it told us this was 50, right? And it told us M was 70. And we know that these are 60. Okay. So this is actually like a pretty common trick they like to use. This is actually good enough. The reason why is because we know these 2 angles, we can solve for this one. What is 180 minus 70 minus 60? 70 plus 60 is 130. And then 180 minus 130 is 50, right? So that means this angle is 50. And this angle is 50. So that's actually enough. So the fact that it gives us 2 separate angles, though. Like it gives us this angle, and it gives us another angle that wasn't corresponding to that angle. But that's fine. We can still use the information that it did give us to prove that, oh, there's at least 2 angles that are the same for these. Okay, hopefully that makes sense. And like this one might have worked, but the problem is like 180 minus 70 minus 60 does not equal 60. It equals 50. So like even if S was like this angle at the bottom here, and like it would actually, like I messed up the drawing and it should have been like these 2 angles should have been flipped around or something, it still wouldn't have mattered because that's not 50. Like it should be 50. In this case, it is 50. And by the way, like you don't need whichever order it says the triangle in, just draw that in the same order. It's like L, M, N. So like this just means the first angle should be L, second angle should be M, the third angle should be N, and so the first angle should be R, second angle should be S, third angle should be T. So as long as you draw it out like that, like L, M, and then you put like exactly, so the middle angle like is at the same spot, those are the corresponding angles. Like the whichever order the angle appears, it's going to be, so like the M is going to be corresponding to T, S is corresponding to M. So just the tips for when you draw the triangles. I've never seen otherwise where it was like, oh, actually M is corresponding with T. I've never seen it. It's just like the middle angle is going to be corresponding, the leftmost angle is going to be corresponding, and the lastmost angle. So you just draw it out like that. Okay. Now let's talk about proving congruency, which is, I don't know if it's harder, but it's like new stuff you have to learn, right? You kind of already knew similar triangles. Now let's go over congruent triangles. Now, congruency, the only way you can prove congruency is one of these four. Now, maybe you think, oh, there's 4 things I have to memorize, like what is SAS? This probably should seem familiar to you. It's probably been a while since your geometry days when you were doing this stuff, but you're like high school. Usually geometry is like their first or second year, and you're probably like third years. So I guess it's not as like familiar, but this should like seem somewhat familiar because most of you are taking geometry by now. Okay, but really, what does this mean? Like, and how do I memorize this? Because it's actually a really easy way and a fun way to memorize this. Okay, so basically, if you think about every single combination of SAS, there's like 2 letters, A and S, and there's like three, I guess 3 spots for them. Okay, SAS. So we're for 3 letters, and you can only use S and A. How many combinations are there? Okay, there's SAS, ASA, AAS, SSS. There was also AAA, right? And also AS, excuse my language, but ASS. Okay, these are the 2. And I'm not counting about like if you like flip something like SAA. I'm not counting about that because it's gonna be the same. Like on a triangle. By the way, A and S stands for side and angle, in case you forgot. So angle, side, like angle and a side. Right. So like if I do like angle, side, that's the same thing as side, angle. It's just like depending on like which direction you're looking at it from. So it doesn't matter. I'll show you what I mean later on. Okay, but it's just no like this. Flipping it doesn't matter. Okay, so the other combinations though, AAA proves similarity. Okay, it doesent prove congruency. So that's all. So just remember, okay, AAA proves similarity, and ASS, or you can think of it as SSA. All I remember is that the SAT is PG, so there can't be curse words on the SAT. So that makes it really easy because, okay, there can't be curse words, so AS is out, and similar triangles is out, so there's no AAA because we're trying to prove congruency. So all that's left is just these 4. So that's a really easy way to memorize this. Just like think about all the combinations of A and S for 3 letters, and then just eliminate the curse word and eliminate similar triangles, which is AAA, and then what's left is just these 4. That's a really easy way to memorize this. Okay, now what do I mean by like SAS? So basically, it's saying the side, the angle right next to that side, the side right next to that angle. Okay, this is SAS, and it's basically saying, okay, if I have 2 triangles, and I know, okay, this side is equal to this side, and then the angle next to, like one of the angles next to that side is the same, and then one of the sides next to that angle is the same. Then, and these are, so this is the same as this one. Okay, this angle is the same as that angle, and this side is the same as that side. Then that's enough to prove that these triangles are congruent, meaning they're the exact same triangle. So if you see this combination where like if you have 2 triangles, and then there's sides, and then there's angles, and there's a side right next to that angle that are the same for the 2 triangles. If you go between them, then these 2 triangles are the exact same triangle. They're congruent. Okay, same thing. So let me just draw the triangles again. I kind of hate how it disappears, but I'm dealing with it. So angle, side, angle, side, angle. I guess works too. It could also be like angle, side, angle. It doesn't matter. But as long as it's like a side right next to that angle and the angle right next to the side, then that's fine. Okay, and angle S, you just like the angle. So this angle, the angle right next to that, it doesn't matter, like this one or this one, and the side right next to that angle, like angle S. Right? If you choose this side, this would be angle, side, angle. Now that won't work because angle, side, that would work. Okay, well, side is all the sides are the same. Okay, hopefully that makes sense. Let's do a practice question. If that didn't make sense, then I think it will make sense after we do a practice question. So try this for yourself. So pause the video, see if you can solve this. Okay, hopefully you try solving it. So in triangles ABC, let's draw the triangles. I know it could be annoying, but I would highly recommend you draw it out. It's just worth the extra few seconds to guarantee you didn't mess up any angles in your head or anything like that. Just a public service announcement for you. Okay, so here's a triangle, A, B, C, and then D. And by the way, I have seen a question where D was like no additional information necessary was the correct answer. So don't just eliminate that, by the way. Yeah. Okay. Anyways, so we have this angles B and E. So we know these are the same. I just like showing that they're the same. Okay. B and E are 27. C and F each have measures. So C and F. So by the way, we have an angle and an angle. So all that's left, remember the four angle, I'm thinking angle side angle, like angle side angle would work. ASA would work. So here's ASA. The other combinations are angle side. Right, we can do angle. If we know like this side or this side, that's enough. Or like this side, if it says that this side is the same as this side, or that this side is the same as this side, or that this side is the same as this, like any side in general, if it says that, then that's enough to prove congruency. Angle won't work because that's similarity, right? So like this angle, this wouldn't work because that's similarity. I think that's all the combinations out of the four, because the other ones are side. That won't work. So we have two angles, right? And the other one is side, angle, side. And we have two angles already. We don't. Then we would need like two sides. We need like this side and this side, or like this side and this side. So we need like two sides and an angle in between them. And I don't think that's going to work, right? It just gave us two angles. We probably just need one of the sides. If you look at the answer choices, yeah, angle doesn't work. That's only one. There's not even like two. It's not like this angle are the same. It's not even that. The side angle, that's not even like two sides. They're making it super easy. Okay, the length of the side is BC. So BC, yeah, and yes, that's angle, side, angle, right? Angle, side, angle. There's two angles. We know these angles are the same. This side is the same, and this angle is the same. Bam, that's angle, side, angle. So we have a way to prove that they're congruent, angle, side, angle, because it's one of the four that proves congruency. So C would work, because that would prove that these two triangles are congruent. Okay. And finally, so we went over proving similarity, proving congruency, but now let's go over how to like actually prove it's a triangle. Because like there's actually like rules for it. There can only be this many, this length of sides for a triangle. If that makes sense. Like the third side of this triangle can't be greater or less than this length. And this is called the triangle inequality theorem. Now, you actually don't need to know this theorem, because for every single, at least digital SAT question I've seen, I remember back in the paper SAT, I think you had to know this, but I'm pretty sure you don't need to know this now. Like you generally don't, but you do need to know the trick that they test you on involving this thing. So here's like a good question to simplify that. So I just want you to try this, because it's better if you like make the mistake and then you'll learn from your mistakes. So I want you to try this and like get the question wrong, and then that way I can tell you, oh, this is actually how you do it. It's gonna stick in your brain much longer. So now that I said that though, you probably won't make the mistake. See if you can like beat me and like not make the mistake. So pause the video, see if you can solve this. Okay, let me solve this question now. The triangle inequality theorem states that the sum of any two sides of a triangle must be greater than the length of a third side. So that's just the triangle inequality theorem. I'm going to explain this as we read on. So if a triangle has side lengths of 7 and 10, which inequality represents the possible lengths of x, of the third side of the triangle? So if we have a triangle and we are told that this is 7 and this is 10, what can be this length? And it's not like this length could be like 1,000, right? Like that's not possible. Like if you think about it, like even if I stretch these two sides to the very maximum, like I just like stretch, it's pretty much a straight line at this point. I can't connect like this 1,000 length side. It's gonna go off the screen. Like I can't connect the endpoints of the endpoint of this line, I guess, to the rest of the triangle. It's not possible. So there has to be a limit to what the third side can be. And if most of you, at least watching this video, probably thought like 7, it has to be a number less than 17. Because 7 plus 10, like any two sides of the triangle, right? So 7 must be greater than the length of the third side. So basically saying, if I add up two sides of the triangle, so 7 plus 10, that must be greater than the third length. So this third length can't be 17 or greater. It has to be a number less than 17. And then you picked A, like that's be a number less than 17. However, that's actually not right. Okay, you are right on the fact that this side length has to be a number less than 17. However, what if the side length was 1? would that still satisfy the triangle inequality theorem? Because remember, it says any two sides of a triangle. It doesn't say that it has to be specifically these two sides, like 7 and 10. It could be that this side length and this side, like 7 and 10. It could be that it's this side length and this side. If you add these two side lengths, 7 plus 1, that equals 8, which is less than 10. So it can't be 1, actually. So there actually is a minimum too, not just a maximum, but a minimum side length for this triangle. Okay, so what is that minimum? I think you probably already like got the answer by now. But so if I like, what I had to figure out, so like 10 is obviously the maximum. So if this isn't the maximum side length, then that must mean 10 is the maximum, like the largest side length on this triangle. So that must mean that this side length has to be like 7 plus this side length has to be greater than 10. Okay, so 7 plus 3 would equal 10. So that means this third side length has to be a number greater than 3 as well. Okay, 7 and because it has to be these two side lengths sum has to be greater than 10. So we can't do 3. So it has to be like some number greater than 3. So maybe 4. Like 4 plus 7 would be 11. That's fine. And that's greater than 10. So the correct answer to this question is actually C. And congrats for the people that did figure this out and got it correct the first time, because this is a really hard question. It's pretty much a trick question. It's really hard to recognize that because most people just assume it's A immediately. And maybe they forget to check out the answer choices, or they forget to consider, oh, might be the lowest thing. But now you know. Now that you've experienced this trick, you won't fall for it during the actual test. So if you see something to do with triangle inequality theorem, like these two side lengths must be greater than the third length, like that, then you know, okay, there's also the greatest length, also the smallest length it could be. And they count for the minimum and the maximum side that this third length could be following this theorem. Last and definitely the least is circle characteristics questions. These like pretty much never appear at all for some reason. They used to appear a ton on the paper SAT. I don't know why. On digital SAT, they pretty much never appear now. But there are a lot of circle characteristics questions, at least what I like to call circle characteristics questions, on the question bank by College Board. So it's not like they're not going to test this. They could definitely test you on this. So I would know this. It's just they don't show up on the actual test for some reason, like at all. But I think it's helpful to learn. There's only been one circle characteristic question, at least what I'm about to go over, one of these questions in like the past 12, 13, I think, around official tests. And that's why there's only in the first module. There's like a pretty easy question, actually. There's never been like a really hard one. But it used to be all over the place in the paper SAT. Yeah. Okay. I don't know, but I'll just go over this just in case it does show up and you know this. So by the way, when I say circle characteristics, I'm not talking about circle equations. Circle equations actually are pretty common. They show up all the time. That might be like what they're listening to is they want to do more circle equation questions for some reason. But I'm talking about like normal circle questions that you can't solve with Desmos. So there's no like equation of a circle. There's no unit circle thing going on. You can solve those with Desmos, which I have like the Desmos guide for it. And I also have a separate video just for unit circles that you can watch on my YouTube channel if you haven't done that already. I'm talking about circle characteristics just for like the questions, like the normal non-Desmos questions that you can't really solve with Desmos from start to end. You actually have to know like a bit of geometry to solve the question. For these questions, I break it down into, I guess, like two sections. There's arc length and sector area, as well as just like random characteristics you have to know. Okay, so it's just, I guess, two different areas. Let's go over arc length and sector area first, which I think a lot of people get this overcomplicated with. It's actually pretty simple if you just know this formula, which is basically the central angle of a circle. Which, so that's just like the middle angle, right? Central angle is just the angle at the center. The central angle. So the angle at the center. Right? It's pretty self-explanatory. So the central angle over the angle 360 degrees. Right? So the entire angles. If you don't know, it's also in the reference sheet. It really tells you here. Right? The number of degrees of arc in a circle is 360. The number of degrees in radians is 2 pi. But basically, the entire angle of a circle adds up to 360 degrees. Okay, so that's where the 360 comes from. So the central angle over the entire angle of the circle is equal to the arc length over the circumference. So it's equal to, so this over like all this entire angle is equal to this over this entire circumference. I know it's not like this entire circumference of the circle. And it's also equal to the sector area. So like this area thing over this entire area. Okay. So if you can't tell already, like these arc length sector area questions have to do with like circles looking like pizza pies. So if you see like a pizza slice type of thing, this is a you have to use this formula pretty much. And I think this, you don't even need to memorize this formula because I think it just makes logical sense. Right? Like if I have, it makes sense that the fraction of this over this is the exact same as this over like the circumference of the circle. It's the exact same as the area over the entire area of the circle. It just makes sense. It just looks like they're proportional to each other, right? Like you just imagine like it should be like, I think it should just click that. Okay, that makes a lot of sense, right? Okay. You can memorize it if you want to. I don't think it's like, I just want you to understand it, just to make it make sense to you. Okay, yeah, it's just like looks proportional. Like draw them out, like just look at them. You should be able to tell. That makes sense. It's the angles on top of the entire circle angle, the length of the circle on top of the entire length of the circle, and the area of that circle, of a portion of the circle over the entire area of the circle. Like all of those are the same if they're like within the same, I guess, pizza slice, right? Like this angle and this arc and the area of this arc. Like it's the same, right? For like pizza slice proportionally to the entire circle. Okay. I'm like going deep because I like want you to understand it. So that way you don't have to like waste the brain power to actually memorize it. I think it's much easier if you just understand what's going on. But it's actually like a really good strategy for questions like this. If you see a question having to do with like a pizza slice or anything, all you have to do is just like mark all the stuff that you do know. Okay, like the question tells you. So it often tells you, oh, what central angle. So if you know the central angle, you already know it's a 360 by default because that's just a number. And let's say it gave you the radius, and you can use the radius obviously to get the circumference because that's like in the formula for circumference and circle area too. So all you need to find the area of a circle and the circumference of a circle is just the radius. So let's say the question gave you the radius, so you automatically knew the circumference and the circle area. And the question gave you, and we obviously know 360, and the question gave you the central angle. Then you can just solve for this now. So I can just like put this in Desmos. I can also like solve for this now. Because I can just put this equal to this on Desmos, and it's going to solve for that for me. So basically all you need to know is like any of these two fractions. So maybe it's these two, maybe it's these two, maybe it's these two. And you need to know 3 of the 4 measures of these. And like most commonly, it's going to give you the radius. So just by, if it tells you the radius, you automatically know the circle area. So really, you just need to like know one of these. Okay. I might not always give you the radius, by the way, but it's just like general strategy wise. So I just like have this formula in your head while you're reading the question. Just like mark off, okay, I know this, I know this. Okay, I can solve for this then. Now you can just solve because you already know this by default, right? You can just solve for that. I'll show you examples though. So let me put this formula like right underneath the question so you can see it while you're doing this. Okay, so let me see. So pause the video once I like show the question in its full glory, I guess. So pause the video, see if you can solve this question, use this formula. Better yet, try to like memorize the formula and like, I guess like use your hand to block the bottom of the screen or something. I don't know. But like try to, like, it's better if you can just like already have the formula, just understand where the formula comes from so you already know it. But anyways, pause the video, try solving it. Okay, hopefully you had a chance to look at it. Let's actually, yeah, let me just keep this here. Yeah, why not? So, circle above has a center O, the length of arc ADC. So ADC, that's the arc length. So is 5 pi. So it already told us the arc length. Where do you know that? X, so that's the center angle. So we already know 100. Okay. What is the length of arc ABC? This arc. Okay, interesting. So we know this obviously. Let me zoom in actually so you can see. So in this formula, let me go to the one top. So in this formula, we obviously know 360. It told us that this was 100 degrees. It told us that this was 5 pi, I think. Or maybe 6 pi, I don't know. But it told us this length. And we need to know like the arc length that was like the other way around, like this one. How can we get that? If you just look at this, like this, the stuff we know, what can we find using the stuff we know? We know these 3. Like what else in this formula can we solve for? Obviously the circumference, right? Because with like these 2 fractions, we know 3 of the 4 values. We can obviously just like put this as X or something on Desmos and just have Desmos solve this for us. We can easily get the circumference. And once we get a circumference, that circumference is just the perimeter of the circle, right? It's just this entire circle. Then we can just subtract the perimeter, like subtract this part, which we already know is 5 pi. I subtract this part from the circumference. Remember like the strategy with the area and volume where you subtract the stuff that you don't want to get the stuff that you do want? You can subtract it from this, and then you can get what's left. That's easy, and then you can just get the answer. Right, so this is where the formula comes in. So this is like a pretty standard process. You just follow the formula. Right, so let's type that in on Desmos. Because who needs mental math? Right, so central angle was My desmos is probably, okay, there we go. Central angle was 100 over 360. You can say like at least this fraction or this proportion should be equal to the same fraction or the proportion of 5 pi over the circumference. I'll put C, whatever, for circumference. And then we can see what the circumference is. And then we can literally just do, now that we know the circumference of the entire perimeter of the circle, we can just do C minus 5 pi. And then this is going to be what's left, so like the answer. Now I'm afraid that, yeah, these are in pi. So I guess we could type in the answer choices until we see which one. I think it's probably like A, 9 pi. Shoot, I'm stupid. 13 pi. Yeah, okay. I was close enough. Okay, so the answer is B for this one. Because like 13 pi, answer choice B is the same as the arc ABC, which is what we were trying to find. Now that's pretty much it. Okay, like hopefully this seems pretty simple to you now. How to solve arc length and sector area questions. And they're pretty uncommon that you'll see this, but now you know in case you do see it. And just one more thing, it's actually like super simple. If you see something to do with arc angle, okay, there's a difference. There's arc length. There's arc length, so like the actual measure of the length of this arc. Also the arc angle, which is different from the central angle. Okay, central angle is like the angle on the center of the circle. But if it mentions something about the arc angle, it's actually really easy. Arc angle is just equal to the central angle. So if it told you that this arc, the angle of this arc is 100 degrees or something, then automatically you know, okay, this is 100 degrees as well. Or I told you this and asked you like, what's the arc angle? Then you just, oh, it's 100 degrees. So the central angle is 100 degrees. Basically, the arc angle is equal to the central angle. I guess this is like another way to say the central angle or something, but I've literally seen questions tell you, oh, this is the central angle, what's the arc angle? And you have to like tell Desmos or tell the SAT what the arc angle is, and it told you the central. Like these are going to be a really easy question, but a lot of people just don't know that the arc angle is the same as central angle. So just in case, you know, and it's always like the one like you can't do like this arc angle is the same as this one. Obviously, it has to be the one like in that same pizza slice. Obviously, okay. That's arc angle and that's central angle and arc length sector area questions. Let's deal with more types of circle questions, and this is even less common that you'll see questions like this, but we'll go over it just in case you need to know them. So if there's a circle on your screen, like the question has something to do with a circle, and it's not, there's no pizza slice, or there's nothing, or like you don't, it's not an arc length sector area question, or like you need more stuff to like be able to solve the question, basically. Like you need more information somehow, even though, because the question doesn't give you enough. I guarantee you, it's one of these four. This is just like with right triangles, where like you have a checklist of 3 things, or circle, Pythagorean theorem, especially right triangles. Let's see one of them applies. It's just like this. It's just a checklist of these 4 things. So you have to memorize this. Actually, you don't memorize the first one technically, because this is in the reference sheet, which is just the sum of the central angle of a circle measures 360 degrees or 2 pi radians, which is literally right here. Right? It says the degrees of arc in a circle 360 or 2 pi radians. So it already tells you that. But I guess you don't need to memorize the first one. I think it's pretty obvious. Pretty much everyone knows this. But you definitely need to memorize these 3. At least I would memorize these 4 as like a checklist you need to go through. If you see a circle and it's like you don't know the answer right away, just like go through these 4 and just see which one applies, like which one could apply, and then just go through that. Okay, the second characteristic of a circle that you need to know is lines tangent to a circle and the radius of the circle form a right angle. So what I mean by that is if I have a circle and there's a line, by the way, a tangent line just means it brushes it one time. Like there's a line that's barely brushed it. Like this isn't tangent. Okay, this is because it's brushed it 2 times. But it's a circle and like a line barely grazes the circle. That means it's tangent to it. So it should say the word tangent, by the way, in the question. So if you see a circle and you see the word tangent, then that's a dead giveaway. Okay, so let's say this is tangent. Like pretend it only touches at one point on the circle. That's tangent. So what I'm saying is this line, the line that's tangent to the circle, and the radius of the circle form a right angle. And this is helpful because like it's a right angle. You can probably make a right triangle somehow, or like use that as 90 degrees, so you can use that angle to solve for other angles, things like that. So again, if you see lines tangent to a circle, automatically you should be thinking, oh, like I should probably draw like a radii, and then that was a right angle, and use that. Okay. Third one is, and I think you like intuitively know this, but it's less obvious. The radii of the circle have the same length. Okay, like all the radiuses, radii, plural, have all the same length. So basically, any triangle that contains 2 radii is an isosceles triangle. So if I have a circle and I have a triangle inside the circle that's made up of 2 of the radii, so let's say this triangle, this is a radius, and this is a radius of the circle. This is a isosceles triangle. A lot of people don't realize that. So like a good strategy when dealing with circles is just to draw a bunch of radii in the circle. Just see if you can form isosceles triangles. You can work with that. Because with isosceles triangles, again, all you need is just one angle on that triangle, and you can solve for the other angles. That might be helpful. Let's say you're trying to find the angle of something in the triangle, and you know, for example, like this angle. But you have no idea, okay, how do I get the other two? You just need to realize, oh, this is an isosceles triangle, because these are radii are the same length, right? So this isosceles triangle, so like, oh, I can solve for these two, because the isosceles triangle, I can just, and we went over how to get the other two angles, but the after one has 80, and like this is the same as that one, I can just do 180 minus those two to get that one. Hopefully that makes sense, okay? And the fourth one is called inscribed angles. Actually I have a diagram of this. Let me scroll down. So inscribed angles is basically when there's the central angle and an angle on the circle, and these two angles share an endpoint of the angle, I guess the ends of the angle, if that makes sense. Like the ends of the angles, they share an endpoint. So again, if there's a central angle, so an angle on the center of the circle, and an angle somewhere on the circle, like anywhere on the circle, and they share endpoints. Okay, they share like endpoints. This means that this angle will always be exactly half of this angle every time. This is called inscribed angles. By the way, it doesn't have to like look like this. By the way, this says if this is like 40 degrees, then we automatically know this is 80 degrees, right? Because this is always going to be half of this. Like the angle on the circle is always going to be half of the central angle if these two angles share endpoints. Okay, and it doesn't have to look like this. It could even look like this is the central angle, and then this is the. It can look like this as well. It's the same thing, right? This is on the circle. It shows the endpoints of the central angle. Then that's fine. Like this is going to be half of this angle. It's always going to be the case. Okay, let's do some practice questions. I think this question is too easy. Let's do like hard ones. Let's do some practice questions. These questions can get pretty hard. So I guess count yourself lucky that you don't see on the actual official test that often, because they can get pretty hard. Okay, so pause the video. Try solving this question and see if you can solve it. Okay, hopefully you tried solving it. It says in the figure above, point O is the center, so we know that's the central angle, basically, of the line of the circle. Line segments LM, L, and the tangent. So right away you see tangent, immediately, oh, right angles. Yeah, these are 90 degrees. Right, you see these lines are tangent to the circle, and respectively, and the segments intersect at point M as shown, like there, and that's 60 degrees. If the circumference of the circle is 96. What is the length? Okay, so I'm actually thinking of arc length sector area questions as well. So it gives the circumference and everything. But we know these are 90 degrees because of tangent. Then that means we can solve for this, right? Because one way you can think about this is like divide this in half, and then it's 30, 60, 90 triangle. Like this is 9 degrees, you divide the 60 in half, that's 30 degrees. 30, 60, 90, that means that this must be 60 degrees. So this entire angle must be 120. Or you can just do like, oh, quadrilateral, it's 4 sides. Yeah, I know, like if a shape has 4 sides, then all the angles add up to 360. You could have done that as well. And 360 minus 90 minus 90 minus 60 equals 120. Basically, we can get the central angle. Okay, and like remember our formula for this, right? If we got the central angle and it totals the circumference, it literally said what the circumference was. We know central angle, and obviously we know that the angle is up to 360. Then we can just solve for the arc length. Right, were we trying to find the arc length? I don't even know if I read the entire question. What are we trying to find? What is the length of minor arc LN? Yeah, we're trying to find L. By the way, it says minor arc is just the smaller, because there's technically 2 arcs. Like there's 2 LNs, right? This LN is also like this LN. So the minor one is just the one that's minor, the one that's less. The major one, if it's a major arc, then it's going to be the one that's bigger. This is minor, so it's this one. Okay. So let's just solve for it, because we already know like the angle, and we know the circumference, which is 96. So let's just solve for it. So central angle, which was 120, we found that over 360. I'm just using the formula we talked about. Okay, equals, no, we need to find this, right? And the circumference 96, 32. So 32 is the answer. That's how you solve that question. I know that might, the hard part about this is like recognizing, oh, tangent line forms a 90-degree angle. But if you know these 4, you just do a checklist. Okay, which one applies? Oh, it's tangent. So we can probably use this. Then the question pretty much solves itself after that. Right? You just have to like mess around a bit, like think about it a bit. Okay, but like I would try to work backwards maybe, or how do I get this? Oh, I need this angle. How do I get that angle? Oh, I need to like get from these angles to get that angle. Okay, that's pretty easy, and then you can go from there. Working backwards helps a lot. Okay, this is the last question we're going to do. This is a pretty hard question. Like I genuinely, this is one of the hardest questions on a test. At least before, like I knew what I knew before. Like I remember trying to solve this question and like taking hours for me to figure it out. So like, don't be ashamed if you can't figure out what the answer to this question is. But try it. So pause the video, like give yourself a challenge, see if you can solve this, and then we're gonna go over it. Okay. Hopefully you at least attempted to like think through this. It says point P is the center of the circle in the figure above. What is the value of X? We just need to find this. Okay, we just need to find X, and like we're given all this. So, right away you probably thought inscribed angles. But the problem is like, how do you get any of these? Because inscribed angle, it just means, okay, this is going to be double of this angle. Right? But the problem is, how do you get this angle? Right, we know these are 20. But like, how does that translate to this? You might think, oh, this looks like it could be 20 as well. And you put 20. I don't know. Like, you have to actually prove it. Okay, you have to prove like what this angle is. You can't just do it. And you probably like try. So remember, like my tip for let's go for the checklist actually, before I like spoil too much to help you connect dots. So first thing, sum central angle measures add up to 360 or 2 pi in radians, but I don't think that helps you much, at least right now, because like there's really no angles around here to add up to 360 anyways. That doesn't help you. There's no tangent lines, so the second one doesn't matter. And the third one, all radii of the circle have the same length. Any triangle that contains 2 radii is an isosceles triangle. So this is we can try using this, right? It doesn't hurt. So can we form isosceles triangles with the radii? So let's try drawing like a different radii. So we have radii here. We can try drawing this. That forms an isosceles triangle. Does that help us at all? We know it's 20. That doesn't mean like we can get this angle. I don't think so. Yeah, like there's no way we can get that angle. Yeah, that doesn't help us at all. But let's try drawing other radii. Okay, another isosceles triangle I think we can make is this. We draw a line from here to here. That makes this isosceles triangle as well as this isosceles triangle. And now we can use this, right? Because isosceles triangle, we know one of the angles in this isosceles triangle, and so we can get the other two. So we know, oh, this is the same as that one, and these are both 20. These are both 20. Oh, that means this is 40, because 20 plus 20 is 40. And then you can use inscribed angles, right? Remember, inscribed angles, when the central angle and basically this central angle and the angle on the circle share endpoints, right? Then the central angle is going to be always twice as big as the angle on the circle, where this angle is going to be half of this one. Have a way to look at it. But we know this is 40. That means that this must be 80 then. And this is the answer. If for some reason you didn't know inscribed angles, this is like a quicker way to solve questions like this. If for some reason you didn't know inscribed angles, you could still solve the question. We know this is 20. That means that this must be 140, right? Because 180 minus 20 minus 20 equals 140. This is like finding this angle from this angle, because it's isosceles triangle. We can get 140. We know this is 140. And then we can use the sum of the angles at the 360 rule to do 360 minus 140 minus 140, which is going to be 80. That works too. Because you didn't have to know inscribed angles. It's like a faster way you can solve questions like this. Okay, that's it. That's pretty much all for geometry and trig on the SAT. And congrats if you made it to the end of this video. You technically learned how to solve 15.55% of the questions in the first module and 12.82% of the questions in the second module. And pretty much every single geometry or trigonometry question that can't be solved with Desmos from start to end, you know how to solve now. And you can watch my Desmos and my circle video if you want to like learn the other questions that technically are geometry questions technically, but can be solved with Desmos. You can watch that. But this is pretty much it. You know how to solve every single question. Now it's just like using the tools, because there's a difference between knowing how to do something and actually being able to do it. Now you just need to practice using these in real time and like being able to recognize, oh, this is how to solve the question faster. But I hopefully gave you a nice framework of like how to think about how to solve questions, like what to look for. For example, for right triangles, or if I see a square root of 3, I automatically know it's going to be a 3069 triangle. For area and volume, let me just try to get the equation of this area first. Okay, and then you can work your way backwards, like figure out like what you need to get. And then work backwards with like taking to the triangles or isosceles triangles. I just need to find one angle on here. Hopefully that makes sense. I give you different strategies you can use and different checklists to run when you see different patterns. And good luck on the SAT.